Well, hello there, everybody. This is Mark D'Antonio. I am here with Daryl Mason. Hey, Daryl.
Hi.
Daryl's decided to join. He actually volunteered to join tonight. It was fun. We weren't sure if we were going to stream tonight. You'll notice there's a few high clouds going over the moon. And you might say, why are we looking at the moon like this? Why can't we see the moon in regular, actually see it? Well, we could. And to do that, all we have to do is reduce our exposure here to a smaller amount, okay, and then we can actually see the moon like you'd see it in the sky. But see, tonight we're doing something a little different. We're actually going to be looking at the unlit side, all right, over here, and we're going to look to see if we can capture another meteorite strike. No, they're not scheduled, but if we can see a little flash, it'll be on this side where we'd see it, all right? So we wouldn't see it anywhere else. Now, if I want to really do that, what we might want to do is maybe go a little to the east and put the bright part of the moon just off the screen a little. Okay, and let's see how that works. Yeah, we're getting these crepuscular rays on our screen, so we probably have to keep it centered.
Darn those crepuscular rays.
Anyway. I know, huh?
I like anti-crepuscular rays.
Exactly. There's some glows here. Yeah, and we're just checking out the moon tonight, just to since it's up and we can't look at any of the other faint stuff until the moon goes down. But while we're here, we'll do some science and we'll see if we can capture anything.
Alrighty.
And that's a great idea, isn't it?
Sure.
Sure is.
Can I say something?
Oh, you can say something. You're on the stream with me, man.
Okay. Folks, when you see the so-called dark side of the moon dimly glowing like that, that is from reflected Earth light.
That's right.
If you were standing on the moon looking up at the Earth, that lunar phase we see, how much is illuminated? It's presently a waxing crescent. Well, if you were on the moon looking up at the Earth, it would be the Earth would be lit exactly the opposite. It would have a dark crescent and then an oblate lit side, and all that reflected sunlight from Earth is what is illuminating the putative dark side of the moon, actually the unlit side of the moon.
Yep, and during the cycle, as the moon continues around the sun, more of the moon will be able to capture the sun's light, and we'll actually see the shadow go to a vertical line at what we call first quarter. And what first quarter means, it's a quarter of the way around the Earth. Right?
Exactly.
A fourth of the way around the Earth. And then technically full moon is second quarter or half. All right, but we call it full moon. And then before we get to full moon, we have that 3/4 point, which we call gibbous. And we have one where the moon is growing in brightness and then waning in brightness. So when it's growing, we don't say growing gibbous, which would actually be kind of cool. We actually say waxing. Again, astronomers love to use terms that will just confuse you. So it's a waxing crescent, to a waxing first quarter moon, waxing gibbous to full moon, to waning gibbous, waning last quarter, because it's the last fourth of the way around the Earth. And so, there's 4 quarters in a circle. So, the first quarter moon is not here yet. When it is, this shadow is going to be up and down, straight up and down. Okay, the moon is still just a little ahead of that point, and so we get a little bit of the curve. We're seeing the curvature of the moon here. Okay, and you see the craters that are also filled here. Now, if I zoom in on these craters just a little bit, what we can do is actually, this is the zoomed area on that waxing unlit side. Okay, but you'll notice, all right, we go over here, all right, and if any of you know what this bright thing is here, that's a test, a little quiz. Okay, we see that on the moon every cycle. It's a very bright area, all right, but you'll notice as we move over, okay, and you'll see it better when you pull out a little bit. All right, okay, this we can see the typical what am I trying to say? The complexity of the terminator on the moon. There's a lot of craters there, and features on the moon can grow larger because there's less gravity And what I'm going to do right now is I'm going to just do this. I'm going to bring it down to a reasonable amount just to give it a little bit of focus, because as the temperature has been changing, the focus has been changing. So I'm going to focus this a little bit. Okay, so I bring it out, as you can see, and I'm going to bring it in now. And get it a little bit better. Yeah, we got the air in the dome is still acclimating, so it's not perfectly focused yet. It's getting there. So we'll just let it acclimate. All right, let me just do this back again.
I bet you love your autofocus, don't you?
Oh, I do. And the autofocus is great, you know, because that was one of the missing things that I didn't have early on when I was doing this. And I implemented the autofocus, and it's in these little arrows right here. And this is 2 times the autofocus, 3 times, 4 times. All right, so this is like if I really want to swing the focus a huge amount, then I can hit 4 a few times, and it literally drives the focuser all the way to the other end in just a couple of clicks, which is kind of interesting. That's something that I've done before, just to kind of reset things, you know. But let's do this. George Archer, welcome. Jim Merrill, I'm glad you joined us. Thank you, guys. Nathan Gardner, good questions. Is there water on the moon? I can answer that question. We talked about it the other night. Hey, Justin T. And hi, Marianne. How are you? So to answer your question, first of all, I want to say to Jim, I mentioned this before to you in the chat. Thank you for coming to SkyTour LiveStream. I'm glad you found us. George, same to you. And Nathan, same to you. You know, that was funny, George. Yeah, my telescope is actually a wide field scope, and so we actually are looking at wide field. So we're not actually trying very hard to look at something in incredible focus. So we generally look at nebulae and star clusters and things like that, things that are really faint. Tonight, what we're looking at, though, because the moon is up, is we're taking the opportunity to do like we did when the lunar eclipse occurred. We are actually overexposing the moon so that we can see the unlit side. And we also see a star right here. All right, and that's how that's how we can actually, if you remember during the eclipse, we saw stars all over the place here when this brightness was so reduced. Well, now it's not. But if there is a meteor strike, it's going to happen here because it'll be overwhelmed over here, even if we're at a normal photographic setting. So now you actually mentioned, let's see, Nathan actually asked, is there water on the moon? Well, you know what? Down here on the south pole of the moon, where this terminator is, there are craters down here that don't ever get sunlight in them because they're deep and the sun only ever hits on the edge down here. So I think that in those craters, that's why science folks thought, well, maybe there's water in those craters. And we did a mission called the L-Cross mission, where we dropped an old booster stage of another rocket that was bringing another satellite to the moon. We dropped it into that crater, literally aimed it right in and just let it impact. It wasn't explosive. It was just a kinetic impact, okay, like a chunk of lead, basically. And the cloud that was thrown up from inside the crater, which was called Cabeus, C-A-B-E-U-S, Cabeus at the South Pole, was enough to be analyzed by a spectrometer on a passing spacecraft that we had, of course, timed to be right there. And we saw water. So L-Cross proved there was water in the permanently shadowed craters on the moon. However, subsequent research later showed that not only is there water in the permanently shadowed regions, there's water all over the moon in many areas. So that was actually good news, you know, because if we want to put a moon base on the moon now, we're no longer constrained to just going to the North or the South Pole. We can put it anywhere we want. So we could put a moon base on Clavius Crater over here if we want to. We could put a moon base near Copernicus over here, or near this white area that I was telling you about before. I said, what's that white area that I was telling you about? And I'll tell you now. It was Aristarchus Crater and the Aristarchus Plateau. Yeah. And yes, Nathan, water is H2O, 2 hydrogens and an oxygen. So I think that it's very important that we find water because we don't want to bring it up there, you know. And Daryl knows, you know, we don't want to bring water to the moon if we don't have to. We want to make it if we can, you know. And that's just what we're going to do. And we can do it by using the water that's already there, you know.
You know, I could say something that's more of a philosophical argument, perhaps. When we were talking about water on the south pole of the moon on that LRO stream the other night,
yep.
Is it okay for us to use that up as a resource? I mean, once it's gone forever.
Yes.
This is sort of like, you know, if we were to try to terraform Mars, but there was already life there, that do we have the right to do that? I don't mean to muddy up the works. I just that occurred to me the other night. The moon isn't living as far as we know, but is it okay for us to use that as a resource and to use it up where then it's going to be gone for good?
You know, that's a good point. In the same way we use fossil fuels here on the Earth, and when they're gone for good.
Yeah.
And on the moon, we couldn't possibly hope to use the water that's on the moon to the extent that it's gone. However, we said that one time about fossil fuels on the Earth as well.
Yes.
And then we grew into the fossil fuels and used many, many more of them. So, yeah, you're right. I mean, we could have to think about that, although we preserve and conserve water for purposes of being able to promote our lives and keep our lives moving forward. However, if we were to look at the overall content of the water on the moon, there's a whole lot of it, and the same philosophical question is probably even more important when we talk about Mars, because Mars may have life, subterranean life under the crust. So we want to be careful about that now, don't we? We want to make sure that if we are making water there, well, then we're going to be upsetting the balance. But how about this? What if we choose to terraform the planet? Now, isn't terraforming going to destroy any existing ecosystems that might be eking out life, or eking out some type of existence? It's going to do that if we terraform. Yep. You know, we've talked about this, by the way. You know, when we talk about terraforming Mars, what does that mean? Well, it's not like in Total Recall where Schwarzenegger, puts these rods into the quote unquote core of the planet, and all of a sudden all this, water vapor just comes gushing out of the planet. You know, it's like, you got to put the water out there. It's not like that. So what are we talking about? What we're talking about is extracting water from the soils, extracting the water from any meager aquifers that may exist on Mars. We're also talking about melting water ice. Mars has tons and tons, probably hundreds of millions of tons of water ice. The polar caps have a lot of water ice in them, as well as carbon dioxide ice. All right? We call that dry ice, Now, dry ice exists at minus 109 degrees Fahrenheit. That's really cold. All right? However, here on Earth, the coldest temperature ever recorded on the planet was lower than that. It was at Lake Vostok. And where's that? Well, it's a couple of miles below the Antarctic freezing terrain down in Antarctica. And at the drill station, at the Vostok station it's called, they measured 129 degrees below zero there. And that's the coldest temperature ever recorded on the planet. And at that temperature, if you were to exhale, all right, you would exhale snow that would just fall to the ground. You know, so you could not exist there. Humans could not. But there's microorganisms that thrive in heat and thrive in cold. See, life is tenacious. It has a way, you know. And as I always say on our SkyTour radio show, life will find a way. And I borrow that, of course, from the movie Jurassic Park. And Jeff Goldblum, the actor, had always said that. You know, he said to, you know, when they talked about life not being able to reproduce because they removed the genetic code, and he said, well, you know, life will find a way. You know, life finds a way. Well, I mean, they said that for a very important reason. They actually said that because in the real world, not movie world, life does find a way. You know, life has a way of exploding onto the scene. You know, and that's radiative adaptation, where, you know, we have a common ancestor, and then you get like 100 species off of that one common ancestor that evolve off of it. Okay, and that evolution is something that will happen everywhere in the universe, no doubt. It doesn't just happen here. You know, so I think that's pretty interesting. You know. Rick W. says he worked on drilling rigs in Wyoming, and it felt like a minus 192 degrees at that. I bet it did feel really cold. And I've been to Wyoming, and you know what? Wyoming gets winter, man. It gets winter. If we think it's tough here in Connecticut, man, in Wyoming, it is just frigid at times. And I've been there twice so far in frigid conditions, and that was only there in September. So someone from Wyoming saying, you haven't been there in the cold. That's not real cold, you know. You know, it's like 12 degrees, you know, it's not cold, you know. Well, it sure is when you're used to 20 degrees and 25 degrees. And when I get to Arizona with the observatory and everything, I suspect that 50 degrees will feel cold to me eventually, you know. But hey,
look up Wyoming windsock sometime. It's a clever little photograph. Somebody took a length of chain and welded it sticking out sort of sideways, and they call that a windsock. And it's a funny picture, that's all.
Okay, cool.
Sorry to interrupt.
No, it's fine, Daryl. You're here for a reason. You're here to add interesting things and to hang out and have fun. I wanted to point out to you guys, if you from before, remember this star I was telling you about? Well, look how far it got from the moon. Now it's here. All right, and you know, the sun set that way, okay, to the right, and now it's here. This, just a few minutes ago, it was here, and it was here when we started the stream, so that it's moved this far. What is that saying? Is the star moving? Well, actually, the moon is moving. The telescope is following the stars, okay? It's not tracking the moon. The moon is very slowly drifting to the east, all right? And if you look at our orbit of the Earth-Moon system from above, you'd see it making a counterclockwise circle around the Earth. And for us down here on the Earth, where the North Pole's at the top, that means it's going to be traveling to the east. So it's a very interesting, we're actually watching the dynamics of the universe right here, right before our eyes, you know. And if I put the arrow on this area here, this will stay there for good. It won't move. The star will stay at the point. But if I put the point right here, on the moon right there, and just leave it there for a few minutes, you'll notice that that bright white section is going to be drifting to the left ever so slightly. In fact, you can already see it doing that, and I'm not moving it. Okay, and now it's already almost off the white. You see that? You're literally watching the dynamic planetary bodies in play. Yep. Right? Look at it go. You know, so this is kind of interesting, and here's what we're doing tonight. We're overexposing the moon for a little while until we move on to other things, only because we want to see if we can catch a meteor strike on the moon here. All right. Now, there's a MIDAS program, MIDAS. It stands for Moon Impact Detection and Analysis System, and they use visual and infrared systems to view the moon in order to catch the impacts. Well, by catching the impacts, what they're doing is they're actually trying their best to quantify how many impacts actually strike the moon. We know that there's craters that are there that haven't been there before. They're usually pretty small, but we captured, during the eclipse, it was right about here, we captured an impact on the moon, and we saw this bright flash, just like bink, and it was gone. Very quickly. In fact, the flash was about as bright as that star, but over here, kind of on the moon. So that impact was from an object that was about the size of a football or maybe a basketball. All right, and it made like a 40-foot crater or so on the moon. Now you might already say, well, can we go see it? Well, no. We can't see a 40-foot crater. And like I said, our SkyTour LiveStream is not designed primarily to look at the moon. It's designed to do deep sky work and look at nebulae and so forth. So I do have a system. It's actually sitting here next to me in the office here. And it's a 5-inch refractor, rich field. I've had it on the telescope, and rich field means wide angle. I've had it on the telescope before, and it's a lens system only. There's no mirrors in it, and it actually makes the objects that we see really sharp and clear. Refractors tend to be a little better at looking at things like planets than mirror scopes like mine. This is a catadioptric or Schmidt-Cassegrain system. However, these telescopes are research grade, and we can do real science if we want to. We actually have another system that is hooked up to it now in place of the refractor, and we're doing some testing with it. Let's see, I don't think you can really see it, but over in this photo, it's just, oh, darn it all. I apologize. Let me just bring us back to that. I don't know why it just blanked out on me there. I was just trying to show you my the system, and it did something silly. So, all right, let's get it back. Okay, so coming back here to the system, what I was trying to tell you before I got so rudely cut off is that right about here on the telescope, which is actually right about here, okay, you can actually see there's another little thing sticking off the telescope right there. It's just trying to see. Well, you know what? It's kind of hard. We have another system up there that does spectra, and it's going to show us the rainbow of the light that comes from the stars. Very important, because that rainbow of light gives us details about the object we're looking at, and we are going to start talking about that once that's already troubleshooted and and working as perfectly as it can be. We have a whole separate system to take the pictures with it. We've had it up and running before, and we'll be able to do the spectra of, say, if it was a cluster of stars, we could do a spectra of the entire cluster right there. And you can see what's going on inside the star. You can see what the star is made of from this. It's a really, really interesting system, and I really enjoy spectra. I did a lot of spectral work when I was getting my degree in astronomy, and I thought that was kind of great, because for me, doing that kind of work, it really gives you the meat of what you're looking at. You can see what you're looking at. It's not just an orange star. No, this is a K5 star. Halfway through the K-type classification, 0 through 9, and it's a K5 because it has certain lines in it that correspond to materials that are expected, elements that are expected to be in the star's atmosphere. You can literally tell what kind of a star it is by looking at that breakup of the light with a spectral system, and that's what we're going to do. And I've identified, and done this before. For instance, I'll give you an idea. You look at Jupiter, and what we look at when we look at Jupiter is reflected light that is coming off of Jupiter's cloud tops, reflected light of the sun. So, what spectrum do you think we see when we look at Jupiter? It's just sort of a giveaway question, because you're going to immediately think, well, the sun, yes, you see the sun spectrum, except not quite. There's something missing when we look at Jupiter's spectrum. Something else is going on. And I wonder if anyone knows what that is. And if you want to answer that, Daryl, if you know it, you can answer it. When we look at Jupiter, what are we looking at in addition? I mean, what do we see in addition to the sun's spectral lines?
I would guess absorption spectra from the elements in the clouds of Jupiter.
Absolutely correct. That's exactly right. So, in other words, if we know what our sun's spectrum looks like, okay, there's absorption spectral lines. These are these dark lines that are in the spectrum of stars. If we know what our suns look like, and it's actually pretty darn dense. There's a lot going on in it. If we know what the suns look like, then if we just subtract off the suns, we see what's left behind, and that is the absorption caused by Jupiter's cloud tops. And what's that tell us? Well, it tells us that first of all, the lines are in specific places for specific molecules and elements. So by looking at these lines that are created in Jupiter's spectrum that aren't with the sun, we can actually see molecules and identify the molecules specifically that are in Jupiter's atmosphere. It's pretty cool. We see, we'll see methane, we'll see ammonia, and believe it or not, the predominant element in Jupiter's atmosphere, the planet, most of Jupiter actually, is made of hydrogen. That's right. Hydrogen is the main element in all the stars, too. And it's the most common element in the universe. So why has Jupiter got all these colors? Well, that's from very, very small amounts, less than 1%, okay, of contaminants in Jupiter's atmosphere, like ammonium hydrosulfide, that causes Jupiter to have these different colors like brown and so forth. And at the poles, the Juno mission sees these brilliant blue clouds. And these are just gorgeous. And it looks like wet paint that's being swirled and finger painted, doesn't it? When you look at these things. And this is really interesting. So I just think it's a very interesting planet to look at. And if you're interested in the Juno mission, that's JUNO, you can actually go see all the raw images. And guess what? NASA has put out a call to have you image process them. And they provide you with the raw images, and you can image process them and then send them back. And maybe you'll discover something new on Jupiter. I mean, it's changing all the time. So it's really quite an interesting thing. I don't know if you've done any of that, Daryl. I've done a little bit of it. Have you?
No, I'm not into imaging. I like looking through the eyepiece. I have seen some beautiful work, though, done by people other than NASA who have accessed the NASA Hubble files, for instance.
That's right.
Have reproduced, or have processed the data differently than NASA did, and have made some absolutely beautiful pictures.
Oh, I know.
Sometimes you see them on the APOD, the Astrophoto of the Day.
Yep. That's right. And while we're here, I just want to take a time to say hello to Nancy W. and Rockstar and Brian Bruce, Rick W. Thanks for joining us, guys. D. Smith, hello and welcome. D. Smith is a regular and a wonderful person to hang out with us all the time. James Dugan from Down Under. And then we have the Angles Black Souls. Is that supposed to be angels? I'm not sure. It says angles, but the Angles Black Soul, not sure. And so I want to welcome you guys here and say hello. Brandy is also here. And it's really good to have you guys here with us tonight. We're having a ball, and we're having fun looking for meteor impacts on the moon. That's what this overexposed moon is all about here. So we can actually see the moon in regular light, as I've said before. All we have to do is bring down the exposure a little bit. Okay, and then we can see the waxing crescent moon here. All right, but if we're going to look for meteors, we have to overexpose that, because meteors impacting here, even when we look at it normally, won't show up. You won't see them. But if we do this, okay, now we'll see them. And the other benefit is we can also see any stars that are nearby. All right, and so we look at this. like this for tonight. I mean, not the whole night. We're only going to look at this for a little while until the moon gets somewhat lower in the sky, and then we'll shift off and go to other wonderful things to see that we'll actually be able to see that aren't going to be overwhelmed by the moon. It's kind of a young moon still, so we won't be overwhelmed. And as I said, it's first quarter, the moon's shadow is going to be straight on to us like this. And that's what people, when I was little, I said, look, it's a half moon. You know, so that's pretty good. So this gives us a chance to just kind of check things out and watch live. Wouldn't it be cool if like a cluster of meteorites hit and we'd see boom, 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 you know, it's like, wow, look. We'd probably be the only ones to catch it besides the Midas program over in Spain. So I think that'd be pretty cool. But this is also a view I like because it shows us the sphericity of the moon. We see that the moon is a ball by looking at the way the shadow curls like this. In a younger moon, the shadow, the lit area is here, okay, and it's even more pronounced. But right now we actually see it. When we get to the first quarter moon, where it's a quarter of the way around its orbit, then we won't be able to see that spherical nature of the moon too well. But this kind of gives it to us, you know, farther away, getting closer, closest, and then farther away again as it angles down. And during the eclipse, we actually noted that it was a full moon at the time. However, the shadow on the moon was curved. And you were looking, because we were directly in front of the sun for the moon, the shadow that was curved on the moon was the curve, not because the moon was curved. It was curved because the Earth is curved. All right? The Earth's spherical nature was given away to anyone who thinks the Earth is flat by looking at the shadow on the moon during the eclipse. So I think that's pretty cool.
Yeah.
Yeah.
And it's actually a projection of the Earth's curvature on the face of the moon from the sun.
During an eclipse, yes.
Yeah, and the ancients figured this out a long time ago. I forget which one offhand, but they did a pretty fair guesstimate of the size of the Earth relative to the moon by the different sizes of the curvature of the shadow.
Yeah.
The Earth being about 4 times the size of the moon, 4 times the diameter.
Yeah. Yeah, and what's interesting is that, you know, there's a lot of theories about how the moon formed and so forth, and it turns out most recently we've discovered that the moon actually isn't alone as being a satellite of the Earth. There may be another one, a very small object, a captured asteroid more likely, that is orbiting the Earth in a very, very strange elliptical orbit. I think it's a really interesting finding because we've gone this far without knowing it was there. And all of a sudden, now we're catching that there might be this moon that we've never seen before orbiting our planet. I think that's pretty neat too, Daryl. I think you see the story. I think you've seen it.
Oh, yes.
Yeah. You know.
Yeah, it's probably a captured asteroid. It's far out past the moon, if I remember correctly.
Yeah, it is.
It flies in sort of a strange, maybe shaped like a kidney bean sort of orbit.
Yeah. I want to welcome Flames of War. Thanks for coming and joining us here. DW, thank you for coming out tonight, hanging with us for a little while. Watch Slowly asks a question, or he's making a statement about, he says, the moon flies through the Earth's atmosphere, says Igor Balyukin of Russia's Space Research Institute. I don't know if that was just a poor translation of what Igor said, or if he really literally means that. And if he means that, then we have to question what the Russian Space Research Institute actually does. Because I'm not sure that
that may be a sort of a misinterpretation. There was some information out just recently that Earth's atmosphere actually does extend out very far from the planet, and like you know, you're talking a near vacuum at that point, but they
Yeah.
say that Earth's atmosphere does go out, you know, hundreds
Yes.
of thousands of miles.
Yeah.
Very tenuous. I
Yeah.
wonder if that's what the guy was actually talking about.
Yeah. I was actually gonna bring that up. That's why I'm saying I was not sure whether he was actually, you know, mistaking that finding. And I'm not talking about watch slowly. I'm talking about Igor Balyukin. By saying that, you know, the moon goes through the Earth's atmosphere, that statement alone is quite misleading. But if you say at the distance the moon is located, there are there's small elements of the Earth's atmosphere as far out as several 100,000 miles, then that would actually be a sensible thing to say. After all, there's no reason that a nitrogen atom can't be out that far, you know, and there's no reason that, you know, that an oxygen atom can't be out that far. So, and there's no reason. So, that I think that finding is an excellent one. The other thing I think is cool, we talked about this the other night, and this stream actually represents, I think, the 6th stream in about a week and a half or so. I mean, we've actually been getting a lot of clear weather, and I'm streaming every single clear night. And I'm really enjoying the folks that are coming in. I'm seeing a lot of new people tonight. And, of course, we have some really great people that have been in here a lot. And they're here, too. But we're seeing some new people, and I really welcome them. It's very nice, you guys, to show up. And I mean, actually, you know what I should do? I should probably just give you a quick rundown of what we're seeing on the screen here, because you have to understand what's going on. This is the title. This is our telescope control system right here. This is me. Hello. Okay, and in the warm room of the observatory. And this is the live image. This is the camera control system. And this is Dome Cam 1 and Dome Cam 2. This Dome Cam down here, okay, or more appropriately right here, is we're riding along on top of the telescope here. And this Dome Cam, we're actually sitting in the observatory looking up at the telescope over our head. This is the barrel of the telescope you see here. Okay, this is the bottom of the fork mount. This is the bottom of the telescope. And it's leaning backwards because we are polar aligned, or aligned with the North Pole. So the axis going straight up through the bottom here and heading out of the dome, you know, straight through, is pointing to roughly the North Star. And so that gives us, that gives you an idea of what we're doing, where we're going. And that means we only have to move east and west, which are over here, west and east. Okay, so if we go east, then the image goes to the left. Okay, and to the right, head toward where the sun sets, to the west. And this is the only control we really need. North and south, of course, north is up, south is down. And because we're on the globe looking out, all right, then when we go and hit west, we head to the right like this, and east we go to the left. Now, can I swap these two? Sure, but I'm not, because I'm used to telescopes working this way. Hi, Katie Q. I just want to mention, yeah, Amanda, I did put out a call to Amanda to see if she was around, and she hasn't come in. She hasn't been around yet. However, we have Daryl Mason with us, and Daryl is always eager to join and talk about the moon and so forth. You've also heard Daryl on SkyTour Radio, which is the radio show that I have on KGRA Radio, and Amanda is my co-host on there, and Daryl has been a recurring guest who comes on to talk about some really cool things in the night sky. And you know what? I would be willing to bet that he would probably be happy to talk about that even now. If you had a question for him, you can certainly ask him. And I don't have an ego to bruise. I'll certainly just back up and let Daryl answer any question that people want to ask him.
Oh golly, thanks for putting me on the spot there.
Oh no, that's okay. You don't have to do anything.
Yeah. No, you know me, I like to talk. You might notice that star to the right is now evidently walked out of the field of view. The dome cam image might be blocking it, but If you ever wondered, Mark talked about this earlier. When we see the sky move, it's moving east to west, and that's just due to the rotation of the Earth on its axis as part of making up a day. But we see the moon, and the moon is actually moving west to east across the sky. And it moves about its own diameter in an hour. And that is actually the moon orbiting the Earth, that west-to-east motion that the moon makes. We were looking at a star earlier, and we could slowly see it moving away from the moon to the right, to the west.
Yeah, it's back. I brought it back in.
Yeah, continues to orbit the Earth over the course of a month. And did you ever wonder where the word month comes from? It comes from the word moon, a month. Month equals a month. The moon takes almost exactly a month to orbit the Earth.
That's fun.
And that's where the word month comes from.
Yeah, they call it a month, and it sounds like you're doing something in Kerbal Space Program, which is a interesting game.
Yeah, that's where, the American Indians supposedly, they were talking distance. They would say, well, me ride horse, 1 moon, 2 moon, that way. They were meaning it would take 1 or 2 months to ride the horse that far to where they wanted to go. It's the very same thing.
Yep. Very cool.
Anyway.
That's very good.
Oh, that's how things work. Or that's where they came from.
Yep. And D. Smith, I just promoted you, so thank you for your diligence in working with us. I meant to do it. I meant to do it the last time, and I didn't. So, D. Smith, you're now a moderator. Okay. So there's we're looking for potential meteor strikes on the moon, and there is a system which is doing that, and it's called MIDAS, and it's based in Spain, and that stands for Moon Impact Detection and Analysis System, MIDAS. So that's pretty good.
Doesn't MIDAS actually, they detect several impacts a day, don't they?
Well, see, they're
on average?
I don't know if it's several a day, but I know that they actually, they actually use more than just a visual light. We're using a visual light system right here, but MIDAS also uses infrared. And you know what? The real data comes from watching how the infrared tapers. This gives you an idea of, for instance, how how much energy of impact was happening or happened with that impact. I'll give you an example. We calculate what's called kinetic energy. It's the energy of motion, right? And the value is 1/2 the mass of the object times its velocity squared, 1/2 mv squared. Old physics type work. Well, when that hits the moon, and then that 1/2 mv squared is the kinetic energy the object has, the impactor has. When it hits the moon, we actually convert that 1/2 mv squared. That energy gets converted to something else, and that something else is generally heat. Energy cannot be created or destroyed. It just gets converted into other things. And so when it's converted into heat, that higher than 1/2 mv squared, the higher the kinetic energy, the more heat will be generated. Okay, so when we look at these impacts on the moon, we look at that little football-sized object that hit the moon. It's made a 40-foot crater. You have to understand, you could throw a baseball at soft powder all day long, and you won't get a crater that's, in that case, probably about 8 or 9 feet across. You'd never be able to make an 8 or 9 foot crater with a softball, for instance, right? Because you could never throw it fast enough to give it high enough kinetic energy to translate to the motion that would actually gouge out that size of a crater. And I wrote a program that actually calculates the size and gives parameters to what would happen if an asteroid strikes the Earth or and you can actually calculate at what angle it strikes, how fast it's moving, and it gives you the energy of the impact. It tells you how big the crater will be, and based on that, we can actually come up with some scientific predictions about what would happen here on the Earth in such a case. And I gotta say, none of it's pretty, and if it's a small, the program, what it does not do is it does not calculate, and it can, I just don't have that written in, it doesn't calculate how much of the asteroid gets burned up by the atmosphere. We can calculate that, and it can fragment an object and tell you how many fragments might strike the ground or whatever, and it depends on the composition of the asteroid. If it's made of stones, like an aggregate of stone, then it'll be one impact energy, generally less than if the impactor, this asteroid was solid iron, which some are. And we know that because I actually have, and I think I put it on camera one other time. I put it on camera, I think it was a couple weeks ago, actually. I showed people the iron meteorite that I have here that we got from an Argentinian fall. We call the asteroid, the meteor strikes, a fall. So this meteorite that hit the ground in Argentina broke up into lots of pieces. And the one I have is, it's got to be, 8 or 9 inches long, and it weighs 1,700 grams. So if you look up, iron meteorites, 1,700 grams is pretty respectable, but it's fairly heavy, and meteorites are valuable. If I were to slice it up and sell little slices of this thing, I can make a killing on people that want to make meteorite watches. They make the face of the watch, out of the meteorite, and it's this beautiful, weird, shiny surface that's just unlike anything on Earth, because it's not. You've seen them, right, Daryl?
Oh, yeah. It's called a Widmanstätten pattern. It's something to do with the crystalline nature of the nickel and the iron.
Yeah.
Makes a really pretty sort of spikes pattern in the surface of the metal.
Yeah.
I own an iron meteorite also. Mine is one of the Canyon Diablos from down at Meteor Crater in Arizona.
Yep.
Yours in Argentina, I think, is the something or other Cielo, it's called.
Yep.
Mine is a little bit smaller than a fist. It looks pretty neat. It's got desert varnish on it. So it's, it's not black. It's kind of a funny brown color.
Yeah.
It's really cool, though, and I have a few pieces, smaller pieces of other meteorites. Little modest collection. There are meteorites out there, people, that are worth more than their weight in gold, literally.
Yeah.
And it's quite a business for some people, collecting and selling and trading them and all that.
I've had so many people make offers on my meteorite, and I just won't sell it. I don't want to sell it.
Mm-hmm.
I was offered up to $1,000 for this thing, and I was like, no.
Wow.
Yeah. I don't even think it's an iron meteorite. I don't even think it's worth that much. I think it's worth between 700 and 800, but depending on how much per ounce the meteors are selling for now. Iron is fairly common relative to, these chondrites are called, or carbonaceous chondrites, and then stony meteorites. There's some very rare ones.
Yeah, I think I paid $350 for mine, and that was a long time ago.
Yeah.
Well, it might be worth $500 or $550 or something.
Yeah. Mine was actually, I hate this, I don't want to say this to you, but I will. And I'm sorry. I got mine, it was free because I had someone give it to me because they were trading me fossils and meteorites for model work. And I was very happy to take meteorites and fossils. I have all kinds of beautiful fossils from this project.
Cool.
Yeah. It was a guy in Colorado, actually. Yep.
W asks, what is the largest meteorite ever found? Was that the one from Greenland? They hauled out and took to a museum in New York.
Was this just recently? Because there was a recent find in Greenland at the northern tip of Greenland, where what was previously thought to be a glacial valley turned out to be a meteor crater.
Yeah, I heard about that. I think that may have been part of the same fall, in fact. But this meteorite it was some Western expedition went there. It was like 100 years or more ago. They found it, big, huge nickel iron meteorite, and they hauled it off and put it on a ship and took it to the museum in New York City. And they think the one that's been in the news just recently may be from the same fall.
I bet you that's true. I do have to. Go ahead.
I'm sorry. I forget how big it is. It was like 11 tons or something. It was a pretty big meteorite.
Yeah. I did want to answer 2W's question. He asked the question about if you could hit a baseball to the moon, all you have to do is get halfway there, and then the moon's gravity would take over. That would be true if the moon was the same mass as the Earth. But because it's smaller, you have to get significantly further away from the Earth and much closer to the moon before the moon's gravity would quote unquote take over.
Right.
So, and what is that value? Well, the moon is 1/6 the mass of the Earth. So that tells you right there that you have to go within I could calculate it for you. I can't do it in my head. But we'd have to go out, we'd have to be significantly closer to the moon before we'd actually be able to see that happen. I'll try and calculate it before the end of the stream if I can. But you see what's happening? It's relative to the mass, okay? So the point where the forces balance between the Earth and the moon is a lot closer to the moon because it's a lot less massive than the Earth. If it was the same mass as the Earth, then halfway is exactly correct.
Right.
So
Tronman says the Hoba meteorite from Southwest Africa is the largest meteorite on Earth.
Okay, 66 tons.
That's pretty big.
Yeah, that's very big. I got to tell you a little story. When I was getting my degree, we actually had a piece of the Canyon Diablo meteorite, and it weighed about 475 pounds. Solid iron. I mean, we're talking about a massive iron meteorite.
Right.
Polished, beautiful. Okay, it was actually finished down and polished. So every nook and cranny is just polished to this really high luster, and you can see a tremendous amount of beauty in this thing. It was just beautiful. So we ended up one night we were working late at the observatory, and I remember a few of us basically said that we're going to pick up that meteorite and put it on the chair of the director of the observatory. And we did. It took 4 of us to lift this thing. And then we had to go and figure out how to get through doorways with it. And we got to his office. We put it on his chair. And when we put it on his chair, what was funny was we went home. And when he came in the morning, there was this giant meteorite on his chair. And you can't imagine the angry calls we got. And he got in at like 6 a.m. So for our laughing and having fun at 2 a.m., we got these calls at 6:10, 6:15. And he was like, "You get in here and get this meteorite off my chair. What's wrong with you guys?" Yeah.
I have not a story like that, but I have a meteorite story also. Okay. This El Diablo nickel iron I have. Well, I leave it in the car all the time. It was in a little cardboard box, and
okay.
I was proud of it and would take it around, show it off. And I left it in the car one day, and it was a hot summer day. And because the interior of the car heated up, the meteorite also heated up, and it was quite uncomfortably warm to the touch. I was proud of it. It was still new, and I took it into a restaurant I hung out a lot that night. And I was up at the diner counter, and I was showing all the waitresses, "Hey, this is a meteorite. Isn't this cool?" And they were afraid to touch it. It was like the Andromeda strain or something. One of them picked it up and instantly dropped it because that thing was still so warm to the touch. They thought it was radioactive.
Oh, that's funny.
And it scared the dickens out of them. Hello, David Schmidt.
Hi, David. David is from Bangkok, and he's a teacher there. And I know that I think Keith from P&K Science and I are still planning to do a class for you, David. I'd also be happy to do a class for you, and as long as you tell me what you want it on and when, I will be happy to do it for you. Long distance from here in picturesque northwestern Connecticut. In another year or year and a half, it'll be being done from the desert of Arizona. And with any luck, we'll actually have multiple instruments at that point to use. We're working on a whole sequence of changes for SkyTour LiveStream. Not the least of which is when you look at the screen here, you've got all this beautiful eye candy, so to speak, which is actually very informative stuff that I require. Okay, we have our dome cams over here, which show us, you can actually see the moon sticking out of the shutter over here. This is the moon right there. Okay, we see the telescope right here, the barrel of the telescope there. So we have dome cam 1 and dome cam 2. Then we have the live view right there. We have the telescope control system, which is right here. And if we move over, because that star is now pretty far away, okay, these are just reflections from the bright light. Okay, this is the unlit side of the moon that will be lit later on in the cycle, and we're just looking for meteorite strikes here tonight in part. All right, so telescope control here, dome ops here. If you recall, I used to have to go out into the dome and spend the time out there doing whatever I could do to stay warm, and I invested so much money in trying to stay warm. It was crazy. But now I managed to spend even more money to make this all a remote system. The only thing I don't have yet is the ability to rotate the dome, but I do have motors. I do have stepper motors, and I do have a system ready to implement. It's just too cold now to go out and install it. I actually need warmer weather to install it, and then I can test it and so forth. It'll be really, really nice. And it's really only temporary because the dome is going to be transferred over to a roll-off roof observatory once it gets to Arizona. A dome is going to be too problematic to run remotely, and I could be running it from 2,000 miles away. I'm going to live out there, I hope. That's what I'd like to do. And I'm going to be able to use this telescope and other equipment that I've been working on, and everything that requires batteries now are going to be fully piped into an electrical system. And so batteries that, the camera, for instance, uses batteries. Okay. And the camera is going to the camera battery is going to be replaced with a little electronic insert that I'm going to make that will actually give it the power it needs. And it'll be just one command to the dome to start up the telescope, start up the cameras, and get everything running program-wise. And then once everything is up and running, we can then open the roof and start up the telescope proper and have it get its coordinates so it knows where it is on the planet. And that actually helps it align itself. But you can't get away without aligning the telescope really, really well. And that's what we did way in the beginning. That's why this all works the way it does. If we go right now and go say look at the Orion Nebula, it'll pop right up in the screen. And it does because of the fact that we're so well aligned. We can also tell it to go to someplace totally different in the sky to look at a bright star. Maybe Arcturus is rising around now. You'll see it out there. And that's all the way over in the northeast. And that's totally opposite end of the sky. And Arcturus will show up in the screen. It'll show up, on this screen. Maybe not directly in the middle, but it'll be over to one side or it'll be nearby. Okay? And if you'll notice, we have some light clouds coming through here. I'm really hoping that those aren't a precursor to a much bigger cloud bank to follow. And I know that I've been hearing Jay Rich, get an intern to rotate the dome. Yeah, there we go. Yeah, that'd be kind of fun. I know that we do have weather coming. I had somebody in the chat say that there's weather coming. And I'm not too excited about that, but you know what? I'm getting some time tonight anyway, and it's a beautiful view. We're doing this overall view of the moon to look for a meteor strike, and later on, after the stream, we're going to go back and just analyze every frame and see if we can see some type of little dot. I'll tell you right now, right here, okay, over right about here, just a few minutes ago, I actually thought I saw right there, a little flash right there. So I'm not sure, but I'll go back and check. And I did not note the time. It was probably within 5 minutes of this time. So that'll be interesting. I'm not sure, though. But we'll see. We shall see. And welcome, Ted Bronson. Great to hear from you. And Julian, welcome. Nice to have you join us. And when I'm looking in the chat, I'm seeing that there's a few people that have been here before, but I'm also seeing a lot of new faces. And I'm glad you're here. I want to welcome you to SkyTour LiveStream. Currently, I have Daryl Mason with me on the line. Amanda Curran, who's my co-host on SkyTour Radio with me, is usually here, and hopefully she'll join us. But if she doesn't, then we shall just carry on as we are, and it's okay. And let's see. Daryl is also a friend of SkyTour Radio. He's been on the show several times. And he...
Hi, everybody.
Yeah, he does a good job of explaining things to folks and having fun. He is a really good, what we call a practical astronomer. He will go out with a telescope and binoculars, and he understands the optical systems. He understands where things are in the sky, and he understands the stuff that we do to try and figure out where things are in the sky, that we may not understand without being like an astronomically inclined. Well, Daryl is. Daryl's built telescopes, and that's one thing that I haven't. I've done. I've actually built a telescope. I ground a mirror myself, but I can just tell you this. It was really not a pleasurable experience.
I have never ground a mirror or lens or mirror. That's a little too involved for me. It's a little too painstaking. I just bought the optics.
Yeah.
I have a house full of optics sitting around here that I need to build telescopes out of.
That's funny. I chose to actually to do this to just, I don't know, I just wanted to see what would come of it and how hard or easy it would be. And it turned out it wasn't easy. It was hard, as a matter of fact. And I was just not interested in going further.
Yeah, I don't blame you. Once upon a time, I mean, if you were somebody who wanted a telescope of your own, and many people ground their own optics.
Yeah.
That was the way it was done. Jean Texereau, Texereau, I believe. He wrote a classic book on how to build a telescope, which is what I used when I built my first one.
Yeah.
And he gets into the grinding and the whole process, and it is extremely painstaking.
Yeah.
But that's the way people used to do it.
Yeah, you have to use a special rouge, it's called, which is an abrasive, and you would use that to actually grind the mirror, and it just wasn't easy. I mean, it was so hard. And we sat there and ground, and you had something called a pitch lap that you had to make in order to, as like a template for grinding. And boy, that was just very painful. Now, today, people use machines, grinding machines, and they'll just take this machine and just grind, and then they walk away. They leave it for days or whatever. That's how large mirrors are ground. They're ground automatically with computer control. The Hubble Space Telescope was ground that way, its mirror. But the problem was the mirror was ground improperly, and the rest of the Hubble optics that was ground correctly and properly made didn't work, and they had to actually give the Hubble basically a pair of glasses. I remember when the first images came back from Hubble and they had these artifacts on them. I was like, what is that? And it was like, wow. And I'd written an image processing program with my friend John Zach, for whom the observatory is named. Unfortunately, John passed away some years ago. And what you're seeing today on the screen was the dream of John and I, to do a live internet accessible telescope. And the internet accessible part is what it'll be when it's in Arizona, and we'll be allowing people to come in and use the telescope on their own, and we'll actually have hopefully more than one setup, so that one telescope can go and be used by someone, the next one can be used by someone, and then we'll have our SkyTour LiveStream telescope that we're using. I just want people to have access, because who has access to a big telescope, Who gets one? It's like, it's very hard to get time on one, and you don't even know what to do when you have it. So you need someone who can tell you how to handle it and how to use it. That's me, okay? It's also Daryl, of course. And then you want to actually figure out, well, what am I going to look at? What am I going to do with it? Well, most people want to just take nice pictures, And the idea is, with camera control like this over here, well, we can set this exposure to anything we want. We can go all the way up to 409,000 sensitivity. Now, that sounds wonderful, except for the fact that I'm going to drop this down for now, just to say 100, all right, and increase this to kind of eliminate some of the noise. Okay, so what I'm saying is, you don't have that flexibility when you go to these services online. I would give you that flexibility. You're going to be able to do anything you want. You're going to have the same control over the camera that you have here. And then a repository where those images will be that you can download, and they're not going to be small. They're going to be raw. These are RAW and JPEG, okay? And the RAW files, depending on the camera, can be up to, well, mine are about 25, 30 meg each image. And that's actually reasonable. It's not huge. It's sort of, could be a lot bigger and a lot smaller. But we pick something right in the middle because we want to actually show people what's going on, give them an idea, and have them enjoy the journey in Vista, and have it do it themselves if they want to. And of course, what I haven't shown you yet is that we have this beautiful planetarium program that's also hooked in, okay, right here. And this planetarium program is currently locked on the moon, but if we zoomed out, okay, you'll notice that the moon it's kind of close to the western horizon now, and we have Orion down here. And as soon as we leave the moon, the planetarium program knows that we've left the moon. When we get near the moon, the brightness, you see, it simulates the brightness thing that happens with the moon. And we're gonna maybe check something out over here in a little while. So the moon is actually on its way toward setting, but we're not quite there yet. And so that's why we're gonna leave it up for just a little longer, because again, we are trying to find some impactors on the moon if we can. There may not be any, but maybe there will be. We shall see. That's the whole idea, is trying to find them. So I just gotta look through the chat and see if anyone else is here that I don't recognize. There is Daisy and Zoe Amethyst. Yes, excellent question. I mentioned it earlier, and maybe you just joined us. There is a program called MIDAS, MIDAS. It stands for Moon Impact Detection and Analysis System. That is based out of Spain, and the MIDAS system will actually be able to and records the impacts on the moon. And so, like, for instance, like tonight, and we have some light clouds over the moon, so that's why it looks like this. Tonight, for instance, they would be looking like we are at this unlit side. Okay, if we were to change this and bring this down, okay, so it was like how you see it with your eye, Well, this is still too bright for you to catch any impacts on the moon, all right? So we have to actually look deeper and deeper into the image. So we get kind of to this part where this is the other side of the moon that's unlit yet, is in the course of the month. As it goes around, this will end up being the full moon facing us, this whole thing right here. As the lit side increases and gets bigger in size. And then at first quarter, when it's a fourth of the way around the orbit of the Earth, then we'll see that's like a straight line right here. Okay, so that said, I think that that explains what we're doing tonight. While we have the chance, we're going to just check out the side of the moon here and see if we can see any impacts occurring over here. But anyway, I think that's sort of what we're doing, and hopefully you folks will enjoy being here. And I want to thank you guys for coming out to the stream and hanging out with us tonight. It's really enjoyable to have some new folks here who haven't been here before. I'm very grateful and I enjoy your company, as does Daryl for sure.
Sure. Mark, you might take note of Du's comment. A little ways up, he said, let me see if I can find it here, 22, 15, 30, right side top, mark small impact. So 22 hours, 15 minutes, 30 seconds, he said he saw something.
Okay, excellent.
So
and where was that side?
Where
was it over here?
He said the right side top.
Over here?
That's how he described it. Upper right, I guess, yeah. Upper right quadrant someplace.
Okay. Well, dude, that's good. So, that's pretty cool. I want Dude to do. Hi, Laura. How are you? I see you're here. I saw you before. Dude, let me know if was it on the left side in the dark or was it on the bright side? Because we wouldn't see anything on the bright side. But if it was up like around here, then maybe so. Now, there's another thing that happens, unfortunately, with our eyes, which is why recording it makes all the difference. We have something called the autokinetic effect. Our eyes will tend to jump around a little bit, and when our eyes jump around from trying to focus on a small object, we may see something that occurs but think it occurred elsewhere. I was teaching an astronomy class in the Arizona desert a couple months ago. I had about 30, 40 people with me, and we were looking up at the sky, and we saw this tumbling rocket body up there, and it would basically flash at us, go away, flash at us again, and it was rhythmic, okay, as expected. And because of the autokinetic effect, when you looked at it, you thought the flashes were coming from different parts of the sky. Because as soon as the flash went away, you started to look around a little bit near it and say, where was that? And then it flashed apparently in some other place. Now, of course, it was moving, but it was moving in a straight line. So we couldn't really predict where the next flash would be. So everybody saw the flashes occurring all in a very small patch of sky, and they saw them in their minds, the way the brain interpreted this, they saw them actually occurring like in random spots within a small area of the sky. They didn't see it moving in a straight line. But if you focused your eyes and you just tried to make sure that you saw that one flash and didn't lose sight of that flash, then what you could see was you actually see the object was actually moving in a straight line. And that flash was the rocket body just flipping over and spinning. And we saw maybe 6, 8 flashes. I caught it on film, I should say. I captured it. Not a video, but it was it wasn't a video per se. It was actually a set of still images. So it's pretty good. But anyway, I think that's a really interesting question about the impactor, by the way. I'd love to see where that was on the moon and do W. If you said it was on the bright side, okay, well, I'll check I'll check it out. I'll check it out. Yeah, you've got some. You're seeing it on larger screens too, aren't you? He said, "I remember I got Gen 2 screens." Hey, I do too. Look, I have 2 screens. Okay, so that's cool. Yeah. D Smith is saying, "Are you buffering?" I haven't heard anybody say they're buffering tonight. So we're actually hardwired into the routers, so we're actually we shouldn't have any more problems. When we were doing this with Wi-Fi, connecting this control system with Wi-Fi to the routers, we would get some buffering issues, and we'd have problems with the throughput from the streaming program that we're using to get this image and everything else we're using out to you. But we've changed that, so now we actually have a much better system when we're doing this like hardwired. So hardwired is better, definitely better. Okay.
I'm sorry, I just heard from Amanda. She is doing a program elsewhere at the moment, one of her music shows on ERRT.
Earth Radio. Our friend Ronald runs Earth Radio. He's really good. I met Ronald for the first time last year. Ronald is a guy that just wanted to get into radio stuff. So what did he do? He got himself a radio show on Earth Radio, ERT, and it's over at Mixlr. So if you're familiar with Mixlr, Mixlr, you can head over and check out Earth Radio, and of course there's a lot of other shows on there. But then what you can do is you can head over and check out kgraradio.com, KGRA Radio, and you can see Sunday nights from 8 to 10. We do a 2-hour show called SkyTour Radio. This is the companion stream to SkyTour Radio, and we talk about all things astronomy over there. We do talk about UFOs. Remember, I am the chief photo and video analyst for the Mutual UFO Network, largest database on the planet of UFO sightings and cases. We have many hundreds of thousands, actually, of cases overall. So I think that maybe what we want to consider is that, or you might want to consider, is that the SkyTour Radio and SkyTour LiveStream are places where you can go to see the live, see the night sky live and hear about the night sky. And Daryl, like I said, will join us from time to time. It's really a lot of fun having him on board.
Thank you.
Yeah, it is. And it's, there's some planets in the sky too, but I think the ones we would want to have seen are set by now. Unfortunately, and I don't know why James Dugan's comment is getting made to be held until review. I don't see that. That's not a problem. He doesn't ever say anything that's bad. I keep approving your posts anyway.
Yeah, me too. When I can beat you to it. Heck, give him a wrench. He's earned it. That will help him post links.
Oh, that's true. That's true. Yeah. Yeah. So I think that for guys like James and D. Smith, I promoted D. Smith and James just now. James will be our longest distance moderator. He'll be in Australia, and we're here in the United States in Connecticut. So you are literally on the other side of the planet, man, which is cool. And you know what? We talked about this before. There's people that say the Earth is flat. However, I think it's really important to consider that guys like James Dugan, who live below the equator down in Australia, when they look at Orion, it's upside down compared to how we see it, above the equator. Well, that's something that simply can't happen if the Earth is flat. So if anyone ever says Earth is flat and you're a dummy for thinking it's a globe, you're one of those globals, globe guys or whatever. Well, I think that you just have to say to them, well, why do people in Australia see Orion upside down? And your flat Earth guy will go, blah, 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 what? Hey, you got any more of that turkey? And he'll walk away. So you'll just give them a brain freeze, and they won't be able to say much. They won't be able to say much. James,
Mark,
you're welcome.
Have you ever? I'm sorry. Go ahead.
I just said, James, you're welcome. And Daryl's right. You were in the wrench. I kind of meant to do James and D. Smith earlier, actually, and I didn't. D. Smith the other night. James, I was hoping to get to. He's been here religiously. He's quite dedicated to us. So you guys can snipe anyone that says anything bad. But you know what? In SkyTour LiveStream, really haven't seen a lot of that. So I guess this stream doesn't foster a lot of people that hang out as trolls. So I guess it's more of an honorary position. But you know what? If you have to use it, you have to use it. So that's pretty cool. BG, welcome.
Usually go to that other place.
Yeah.
Mark, have you ever read any books by Terry Pratchett, the Discworld books?
No, I have not.
Oh, you should read those. They're delightful books. They're called the Discworld novels. There are, I think, 41 of them.
Mm-hmm.
Terry Pratchett was a British author. He passed away a couple of years ago. He got knighted for his contributions to the United Kingdom. They're very funny books, and I have always wondered how much Terry Pratchett inadvertently did to promote the flat Earth, because on Discworld, Discworld is flat.
Yes.
But he did it as a joke. He did it, I think just to make it funny. But I wonder how many people might have took him half seriously. In the Discworld, it's round. It's shaped like a disc.
Yep.
And 4 giant elephants are supporting it on their backs, which in turn are standing on a huge giant turtle flying out in space. That's Discworld, but that's just the background, and they're very funny and entertaining books. You might enjoy them. I bet you would.
Yeah, and what's funny, thank you. I'll check those out. What's really funny, and this is something that I've often thought of, because when people say to me, is there an edge to the universe? Does the universe end? Well, we think it's over 90 billion light years in diameter. And that comes from a study of the time it takes the light to get here from the farthest distance we see, which is about 13.2 billion light years. But we also know that the universe is about 13.8 billion years old. So that said, we look, for instance, and say, well, what's beyond the edge? Well, when we look out as far as we can possibly see, we're looking back in time. Because the distances are so vast, it takes light a long time to get here. So every single star we see, we see at some point in its past. The sun we see 8 minutes ago. All right, when we see the sun. The moon about a second. Stars anywhere from 4 years, like Alpha Centauri, to 3 or 4 or 5, 6,000 years ago. For the ones that are relatively nearby in our galaxy. But then beyond that, we see stars that are maybe, at least 60 million, 80 million years in the past, because they're in galaxies that are that far away. In our galaxy, we'll never see a star that's more than about 100 to 150,000 years in the past, because it's like 100 to 150,000 light years across our galaxy. So if we could see all the way over to the far side of the galaxy, we'd only see about that far back, However, again, you got to go to the look at the galaxies that have this massive amounts of stars in them that are very, very far away. The Andromeda Galaxy is 2 million years old, and as far as we're seeing, its light is 2 million years in the past. You know, and that's basically saying that the light that left there now left there 2 million years ago. You say, what was happening on the Earth 2 million years ago? And you can go through a whole process. I'm actually developing a talk that talks about the Earth in the stellar past and how it looked at the time when light just first left some of these stars. Really kind of interesting, like Betelgeuse, 492 years in the past. Okay, it might already have gone supernova. We expect it will. But that light chain, that train of light coming from Betelgeuse is still coming. And when it goes supernova, then we will see that light train eventually reach us. And that is such a really neat concept if you think about it. Because if you could see the instantaneous positions of these stars, like right now, some of them won't be there anymore. They'll just be a remnant from when they exploded at some time in the past. But the light that is on its way to us hasn't reached us yet to give us the message that it did. See what I mean? I think that's a really interesting finding, And once again, these spikes that you see on the moon here, these are just reflections, okay, off of the very, very bright moon. We're actually, like I said, we're doing this. I'm going to turn that down. That's a little loud. Some of these songs get a little bit loud, okay, but we're actually just doing this to show the unlit side of the moon so we can look for meteors tonight that might strike the moon. And DW says he saw one possibly over here, and he gives the time up in the chat here. When you play this back, you'll be able to actually review the chat as well. Because it's actually moment to moment recorded, and you will see the chat played back too, as you know, within YouTube. So you can do it here as well and see what's going on. Yes, sirree. The triple star system, DW, that's you're talking about Alpha Centauri? Yeah, that's actually a triple star system. We have an A and B component, which are kind of similar stars to the Sun. And then far away from both of those, there's another star that may very well be gravitationally bound to those two stars called Proxima. That's a little tiny red dwarf. And usually we talk about these different spectral classes of stars. The hottest and bluest are the O-type stars. Next come B-type stars, which are blue. Then A, which are white, kind of like this color of the side of the moon here. And then we have F-type stars, which are slightly yellowish white, and then the G-type stars, like our sun, which are a little more yellow. And then we have the K-type stars, which are kind of an orangey star, a lighter version of this color over here. And then the M stars, which are a red and orangey red, kind of like these numbers. Okay, and those are all the different types of stars that we see, and the color typically tells us the temperature. A bright blue, like the O's, they're the hottest, they're the biggest, and they're the bluest stars in the universe. Consequently, they also, being the most massive, don't live a long time. They last for several 100 million years at the most, and then they almost always end with a supernova. So they always go out with a bang, So, the brightest stars live twice as fast. B-type stars are stars like those in the Pleiades, which are very blue as well, but not as bright blue as an O. And then the A stars are stars like Vega in Lyra, the constellation Lyra, which is a summertime constellation that we will be looking at a lot in the summer. And those stars are then the A-type stars are from there on down to the A's, the F's, the G's, the K's, and the M's are pretty much what we accept as potential stars that can harbor life under the right conditions. And so from A-type stars on down. So that said, we have the F-type stars, and we have the Gs, which is the Sun. And within each of those letter designations, O, B, A, F, G, K, M, we have 0 through 9. So we can have a G0, we can have a G3, a G5, a G9. The Sun is a G2 type star. And then based on where they are in their point in evolution, their own evolution, we could actually have a different indicator to tell us where they are in their evolution, right? If they're doing normal hydrogen fusion into helium like the Sun, then they are given the name of a dwarf. They're called a dwarf, and it's designated with a Roman numeral, and that Roman numeral is 5. Okay, the Roman numeral 5, or the V. All right. So that said, we have that's called a luminosity class. It's basically something that speaks to the evolutionary state of the star. Okay, so then stars that have finished fusing hydrogen into helium can also begin fusing, say, helium into carbon, or maybe carbon into nitrogen and oxygen and fluorine and neon. Okay, all the way up to iron if they're massive enough. And iron is number 26 in the periodic table. Okay, and that location is the end state for stellar fusion in normal cases. You can't get elements higher than iron in the core of a star through normal processes. And I think that's really an indicator that a lot is going on that we didn't understand at one point. Now, the rest of those elements in the periodic table come from supernovae, high pressure, causing instantaneous generation of these other elements, some of them. And another process that actually creates elements in a star is one called the S process. And the S process has to do with something called neutron capture. And that means this. If you, and by the way, good night, Marianne. Thank you for joining us tonight. Marianne is a police officer in Gilbert, Arizona. And I did a ride along with her when I went out there for 10 days. And I got to tell you, I never worked harder in my life. Okay. She was really, really excellent. Anyway, so the S processes we're talking about, these created a lot of these other elements in that we see in the periodic table. And the way it works is under the pressures, all right, that occur in a star, sometimes when a star makes a new element, it'll then add neutrons into the nucleus of an atom that it makes. So we can get, for instance, a carbon-14 or a carbon-12. When we might just have a carbon atom, we can add neutrons until we get another variation of the carbon atom, which is called an isotope. Add neutrons, you get an isotope. We haven't made nitrogen or oxygen, okay? We've just made a different version of the carbon atom. And it takes a long time, but sometimes the neutrons in the nucleus can be converted to a proton. Maybe one, maybe two. And neutrons and protons are made up of more elementary particles called quarks. So when you have, and quarks are known as up and down quarks, okay? So a proton is one particular set of quarks, and the neutron is another particular set of quarks. And they come in threes, up or down. So, for instance, you have an up, and a down quark, all right? And if you want to change the particle, all you have to do is change the up or down of one of those quarks, all right? And for instance, I think it's two up quarks and a down quark for a proton, and then for a neutron, it's 2 down and 1 up. Well, if you change one of those downs to 1 up, you get a proton, and that happens in these atoms during this S process. And the S process now, if you add another proton to the nucleus, Well, guess what you've done? You went from a carbon atom to a nitrogen atom. And this process happens across the periodic table for a variety of elements. And what that means is that it takes a lot of time for it to happen too, but it will actually create the additional elements that we see in the periodic table in part. So we have supernovae, we have these S process, supernovae through this other process like the R process. It's called R, meaning rapid, S means slow. The R process is this thing that happens during supernovae where additional elements are smashed together to form heavier elements. And we get some of those out of that. We get some of these elements in addition. We also see that sometimes neutron stars can merge, and that can generate more elements. We have merging black holes that generate strange effects. We get gravity waves from that. We get white dwarfs that go nova, basically, because they gather more mass on their surfaces, and once they get to a special magic number, which is 1.44 solar masses, then they will explode, either obliterating themselves or just pop off that layer of gas that got onto their surface. And all the time, things are being made. New things are being made. So I think that's pretty interesting. And yes, merging neutron stars, Jay Rich, might be where we get gold. Okay, and maybe all the gold in the universe came from merging neutron stars. And it's kind of odd when you think about it, but the concept of a neutron star, the concept of a white dwarf, really, really interesting. The surface of a neutron star is very dense. It'd be as hard as a billiard ball, you know, but it's all these compressed neutrons that are very, very much smashed together. But if you have several neutron stars that are, or a pair of neutron stars that are orbiting each other like this, and you can see in the operations view there, when they collide, they may begin to connect and touch, and then bam, when they merge, that can generate not only another massive amount of energy, a massive energy burst, it can actually cause more elements to be made. And these elements, now you might say, well, that happens, say, way over there in another galaxy, or you know, maybe at a far distance in our galaxy. How are we ever going to see those elements? The answer is the universe has time, in a time of plenty. And so over time, when things happen, there's nothing to stop the movement outward of an exploding star, for instance. It'll just keep going, and keep going. Eventually, it'll reach us. You know, eventually it'll reach us. You know, or our location in space where maybe a solar nebula it was occurring, you know. And you know, where the solar nebula was in the original, when the original universe was being made. So that said, I think that maybe, and maybe that's something that would be interesting for you guys to look into if you were interested in that. And I just want to, I'll just answer a question here. I'm looking in the quote. I'm sorry, in the chat. Okay, you're asking, Dew's asking, what is a super flare? Well, okay. Our star is a fairly quiescent star. It doesn't really have a lot of flare events that are deadly to life on Earth. It could, but it doesn't. Sometimes a flare can be extremely energetic. Usually it could be associated with something called a coronal mass ejection, where you get an awful lot of this plasma that's also, you know, coming off the star, very, very high power, high energy. And this massive stuff, if you look in the operations little camera view, this massive stuff can get blown off of the star. And then it moves through space, not at the speed of light. It's slower, okay, because it's actually mass, it's particles. And then it comes to the Earth, and if it strikes the Earth, then it could actually cause disasters here. Usually, coronal mass ejections happen, you know, on the sun at times. There are stars where this happens a lot. And there's different classes of flares. And some of these flares, for instance, can be, well, an X-class flare, for instance, is a very, very high energy flare off our sun. And we don't ever see super flares off of our sun, right? We don't have those, but some stars do have them, and usually they're associated with stars that have a very high ultraviolet output. Okay, and sometimes the flares exist only in the ultraviolet, only in the X-rays, which are even higher energy than the near ultraviolet stuff. If you think about the spectrum, okay, if you look at the operations camera, in fact, I'm gonna try something here. If I just do, let me just grab something. Let me just do this for now. Okay. If you look at the operations, our spectrum, say it goes from here to here. That's what we see. Okay, we see a spectrum this big. Okay, this is our one side and the other side. Okay, now imagine now that this is the blue side and this is the red side. Okay, past the red side here. Okay, or wait, no, this is the blue and this is the red. Past the red side here, we go into the invisible light. We quickly get to what's called infrared, right? And then we get to radio waves and so forth. These are longer wavelength, very long. Think of long ocean waves, okay? Very long wave. But then on the blue side, this is where the dangerous energy lives. So we see everything with our eyes that's in between here, okay? But at the blue end of the spectrum, where the light is very blue, it then gets to the ultraviolet range. The ultraviolet range is not visible to your eyes. Okay, and beyond the ultraviolet comes X-rays and so forth, and X-rays are very, very high power. You know how it is. You can't get a certain number of X-rays a year from the dentist. You can't get medical X-rays, beyond a certain number, because X-rays damage the cells. They're like bullets going through the cells, and we found that those can cause cancers and other things. So X-rays are very powerful. And most of these high-power flare events are going to be in the ultraviolet and X-ray realm, where it's absolutely downright dangerous to be around anywhere near a star that's doing that. Give you an example. Some of the stars that we've talked about in the past give off a lot of these ultraviolet flares and ultraviolet energy, okay, in general. But some of them give off even more, and they're very, very poorly understood stars in a sense that we don't really know whether these stars are responsible for more things that we have seen in the past, such as planetary nebulae, the end of stars. And those stars are called Wolf-Rayet stars. They're very massive stars. They ionize gas around them for many light years, and that process will cause the atoms in the gas around the star to glow. Now that happens also with white dwarfs, okay, but it also happens with Wolf-Rayet stars. And Wolf-Rayet stars have powerful, powerful stellar wind. And what is stellar wind? It's protons and electrons moving out from the star at high, high speed, all right? And those are like bullets that would be hitting you. And these bullets would actually be something that could kill you if you were anywhere near it, So I'm very happy to say that we're not, and I'm just going to move this so we got a little bit better placement here.
I heard once that there are some, what would you call them, cosmic rays? They have as much power as a thrown softball.
Cosmic rays?
I think it was cosmic rays. It was one of the energetic particles or rays. Had as much energy in it as a hard thrown softball. Think a fast pitch softball game.
Mm-hmm.
I'd hate to think it'd probably just go right through you if it hit you, but that's impressive.
Yeah,
to me at least.
Well, yeah, just so people understand, people are thinking, well, a hard softball, throw it as hard as you can. Okay, so it bounces off a tree. Well, how hard is that? Actually, we're talking about an atomic-sized particle here. with the same energy in it, energy of impact, that a hard softball would have. So
Exactly.
now you can see the difference, okay? We're looking at something millions of times larger than that particle, and it has an equal amount of energy to this softball that can be pitched by the fastest softball pitcher on the planet. Now that wreaks havoc on cells, okay, as it goes ripping through you, and they rip through you. So we're talking about, and I just want to make sure that people understood that analogy there. That was really kind of a key thing there that you mentioned. So it's really an interesting, it's actually a very interesting conundrum. You know, what do? We want to observe the universe. We want to put up stronger telescopes. We want to leave the planet. But if we leave the planet, we're going to leave the protection of our atmosphere and magnetic field, which protects us from the high energy ultraviolet. It doesn't really protect us from the cosmic rays, you know, and it certainly doesn't protect us from, neutrinos, which are other particles that are very, very mysterious particles. They come from everywhere in the universe, with no specific source, yet the sun, it streams neutrinos. It comes from everywhere. These neutrinos, they come from everywhere. Very interesting, because neutrinos can go right through the Earth relatively unimpeded. Very hard to capture. To capture neutrinos, we got to actually build neutrino tanks down inside of mines, and fill the tanks with special water to capture the neutrinos rushing through them. That's kind of interesting. It is not an eclipse occurring over here, folks.
I was about to say.
Yeah, I believe that we are looking at the moon now passing behind the dome. So I'll have to go move it. Actually, you know what? Instead of moving the dome, why don't we do this? Why don't we say that we're going to go check out something else? We've been doing the moon for the night so far. And Jay, I'm glad you're enjoying it. Jay Rich is saying, wow, you know, talking about some cool stuff. Well, yeah, it's a lot of fun. We're having a good time. Let's go into our planetarium program here real quick, and let's take ourselves off the moon. As I pull away, you're going to notice that the moon is a lot lower to the horizon than it was. See, we've been really zoomed in here. So now let's go up and see if we can actually check out our wonderful friend, the Orion Nebula. And let's just go there and see if we can get there. Maybe we can. Let's see. Yep.
Mark, where do gamma rays come from?
Gamma rays are interesting. Gamma ray bursts that we have seen out there. There are stars that and galaxies, very, very powerful, the center of galaxies that actually generate gamma ray bursts. Gamma rays are very directional, and they're actually dangerous. They're very dangerous to us. So we have to be careful about gamma rays and how we actually, when we go out into space, for instance, we have to be really careful. So energetic galaxy cores can generate them, and I know that there's gamma rays from black holes and other very, very highly energetic events can generate them. I'm actually going to do a 10-second photo here. What I'm suspecting is that the dome is still in the way a little bit, so I'm going to move us over a little bit, actually, the other way. I'll take a 10-second photo at 8,000 ISO. I think we are going to have a little bit of a problem. I may have to actually go out and move the dome, in which case, Daryl, you'll probably have to, fill in the dead air for a few minutes while I go do that.
Okay.
Yeah, see, we got the dome is in the way. I have a red light on inside the dome for the express purpose. When I take a photo, I don't need a red light on in the dome because I'm not out there. But the red light's on so I can see when I have the dome interfering. Because with the telescope, you can never be sure that it's interfering or not. If there's any kind of a red bleed, all right, then it is. However, I also want to say that when you look at just the regular view, and I'll go into a video mode here, all right, when you see a regular view, you'll notice there is a little red here, and down here you can't see it because it's behind me, but there's a little red edge, and that's actually what's called amplifier noise in the camera. Okay, it's a little bit different. It's still red, but it just happens to be affecting that part of the sensor. All right, so what I'm going to do, Daryl, is I'm going to run out and move the dome. So you know how to dance. Just do a little dance.
Okay.
All right. I'll be right back.
Very good. Let's see here. So hi, everybody. Hello, them all. Golly, what do you want to talk about while Mark's gone? Mark's looking at Orion now. Looks like to me, that looks like the trapezium, the 4 little stars in the center of the Orion Nebula. Ted says, Daryl, why don't they have replacement equipment standing by? Ted, I would have to guess it's a matter of cost. You know, they could duplicate the whole electrical network across the country and have it on standby, but that is a vast expenditure. A lot of our infrastructure is outdated also, which makes it more prone to failure. You could liken it, you know, if you've ever heard of an EMP attack, electromagnetic pulse, it could be like that. You know, that's on purpose, supposedly, that they're just going to knock us all offline and go back and live in the Stone Age or something. It could have massive effects, and it could kill a whole lot of people if something like the Carrington event happened nowadays. And what else? Anybody have any questions? I can try to answer them real quick. I'm on lag here, so bear with me. See you, David. Thank you for stopping in. D, I've had a lifelong interest in astronomy. I got my first telescope when I was in my early 20s. I had a paycheck burning a hole in my pocket. I've been doing this for going on 40 years now, not quite 40. Once I hit 40, I'll start saying going on 50 years. You know how that goes. Yes, Julian, they are. Gamma rays are like at the far end. Gamma rays are past X-rays. They're extremely energetic, and they're bad news any way you look at it.
That's true. I am back. Okay, I'm going to do a 15-second shot at 8,000 on the Orion Nebula right here. And then, you probably saw the dome move on the Dome Cam 2. Then I'm going to actually move us to the constellation Leo, which is directly overhead, and we will probably see some very nice galaxy imagery. See, this is what it was before when we saw the Orion Nebula. This is with the dome in the way, and this is without the dome in the way. So quite a big difference, right? And actually, I've got some filtering going on right now. Well, not here, but if I want to do a little image processing, this is a little processing to kind of show some of the modeling in here, which is kind of nice, you know. So you got that, and then I'm just looking at the star quality, and I'm thinking maybe I think we're okay. We're seeing very, very faint objects. That's good. That's good. All right, so we're going to leave that alone. I think we're doing reasonably well on this. Okay, and so I'll again, little processing. I'm going to turn off some of that. Take this processing back the other way. Right, and bring the color correction up a little bit. There we go. Take that. We can also sharpen the image a little bit, you know, so this is a little bit sharpened. And you can see the difference from this versus this. It's very subtle. Right, there's the unsharpened. There's sharpened. See, I tend to leave the sharpening off, so it's pretty cool. So, we are in Orion at the moment, poking around in there. And I am interested in seeing, we have 49 people watching. Thank you for joining us, guys. I'd love to see you, you know, in the chat. If you guys chat with us, we can give you a shout out there. But not a whole lot of people will tend to do that. Of course, I think that the YouTube thing is kind of broken because I've watched people chatting up a storm, like Tony the Night Owl. Ted Bronson's been talking a lot. Amal's here. You know, Julian's been saying a whole bunch of things, you know, and DW, of course. And they're not showing up in the participant list, and I do not understand why. Something's not right there, you know. And then look at Dee Dee. Dee Dee's here. Dee Dee's always visible in the chat, in the participant list, and I don't see her listed in the participant list. You know, there's something not right there. We'll have to figure that out. It doesn't hurt anything, but I don't want to miss you, you know. I want to say hi to Cindy Murphy, who's joining us. That's, as far as I can see, a new user. Melanie Cravens is here. And there's a few other folks here we talked about that have joined us. I know Daryl, I don't know if you saw someone join us that I haven't mentioned yet. Maybe you did. Maybe not. You are still there, aren't you, Daryl? He's on mute.
I was on mute. Sorry. Yeah, hi, I'm here. Cindy Murphy is new, and I bet there are some other ones.
Yeah.
I got engaged in conversation with them all, and I've kind of missed a couple of them.
Okay.
Somebody said they had me on their television.
Yeah, that's he said we had us on 2 screens actually.
Yeah,
which is kind of cool.
I said I didn't want to be on TV, so.
Well, you're not running a camera, unfortunately, you know, so.
Right. Oh, that's a fortunate thing, believe me.
Oh.
It's like I told them in there, I used to be so pretty, but I used to have a beautiful head and naturally curly hair, and now I have a really good case of male pattern baldness. So if I let it go curly, I look like Bozo the Clown now. And that's why I don't have a camera, people.
You know what I say about that?
What?
I can tell you this. I decided a long time ago, it was about 24 years ago, I had to have brain surgery. You know, I do everything big, you know, heart surgery, brain surgery. Well,
I remember you talking, yeah.
Yeah, and I didn't want to shave my head for the brain surgery. I wanted only to clear the area on my head where there was hair in the way and leave the rest. Well, I ended up looking like some type of monk before the surgery, and they said, "You want to just cut it all off?" I said, "Yeah, I'll just cut it all off." And why didn't I do it? I was worried that I was not going to be able to grow it back. I had this big giant scar right across the top of my head, which I do, but as you can see, it did grow back, and it grew back with a vengeance. So I don't suspect I'll ever have to worry about the baldness part.
Well, you're a lucky guy. Yeah, oh God, what can I say? I don't know of anybody bald in my family on either side, yet somehow I got lucky, I guess you'd say.
Well,
I don't know.
I mean, saying I'm a lucky guy, I mean, I'll trade your male pattern baldness for my brain surgery.
Oh,
you
no
know?
thanks.
Yeah.
I wouldn't want to go through that.
Yeah.
I hate surgery anyway.
Yeah.
Yeah, well, keep it and enjoy it while you can.
Oh, well, I'll have it, I think, forever. This isn't falling out at this point, you know? So,
that's what I used to think.
Oh, really? Oh, well, maybe I have something else to look forward to then.
Hey, carry on. I'm sorry.
No, you're fine. You're fine. I'm heading up here for just a second because I want to show What's right above the Orion Nebula is a really cool nebula. It's actually, I think, one of your favorites, Daryl. And you know the one. It's the Running Man.
Sure.
Which is right up here. And I did some really beautiful shots of the Running Man that folks remember. And I'm just going to do 15 seconds at 25,600. I'm going to bring it over a little bit. Head a little more toward the west. There we go. Now we take a picture of it. The Running Man is a reflection nebula, so it's light that's reflecting, for the most part, it's light that's reflecting onto minute dust particles, and those dust particles are scattering the blue components of the light, and we see it as blue. It's really interesting stuff, you know, and so when we look at the Running Man, we see predominantly this, and this is what we'll see without any kind of processing. But if we add some processing, then we see that we can make it look a little better. And we did processing in a different view, a different actually collection of multiple shots of the Running Man. And they absolutely look gorgeous. We got a beautiful Running Man. And I'm going to drop this. I'm going to just show you right here. We're going to drop this down and do some dynamic processing here just to kind of show what I mean. Okay, so in the Running Man, okay, this is a blue part of the nebula. This is the reflection part of the nebula. But you'll also notice right about here and over here, you'll notice that there's some red in here. And that red actually is this beautiful purpley reddish area that's actually what we call hydrogen alpha. It's glowing hydrogen atoms, okay, interspersed with the reflections off of these tiny little microns sized particles that are in the nebula. And this is dust that it's reflecting off of, but then we have the gas also that's glowing on its own from the ionization that these stars are causing to happen in the gas. So this is a reflection nebula predominantly, but we do see a little bit of this hydrogen alpha region in there. And if you look at the Running Man Nebula from Hubble and other photos, you'll actually see these areas a little bit better. Alas, we're on the Earth, not above the clouds, not above the atmosphere. So we have the atmosphere to contend with, unfortunately. But, you know, that's what happens. So I'm going to just take us back to, on the view, we're going to take us back just a little off the processing that we used here, because I want to be able to show us other things later as we move forward. So I'm going to set the defaults, so it's going to look a little bright. All right. This is the standard view, okay, and we will come back to this in this view often. So back in our main view here, the view of the telescope, we have the Orion Nebula below, and with the Running Man here. Now I think the moon is still up, but I want to show you what happens if you try to do something very, very dim. All right, so we're going to go to now our Planetary program, and we're going to come up here to one of my favorite little nebulae, which is right there. You can see this is Alnitak. Okay, Alnitak is the left star in the belt of 3 stars in Orion, which you see right here. And Orion is seen with these lines. You can see this, okay? All right, Rigel is heading towards setting right now. Betelgeuse has a ways to go. And then Alnitak, Alnilam, and Mintaka, the 3 belt stars, will be up for just a little while longer, okay? But while we're here at Alnitak, and while it's actually kind of low in the sky, I actually want to take a photo right here of this area, because I want to see the Flame Nebula right here. So let's go see, as we're moving, we're actually moving now, and there is Alnitak right there. And as we move over and lock in, I'll bring up our telescope control, and that'll give me a chance to either let the telescope tell me when it's ready. We're ready. I mean, I could wait for it, but I don't want to, so I'm going to stop it right there. And then I'm going to take another 15-second photo at 25,600 sensitivity. Now, it's in the murk. It's lower in the sky. But we will see what happens. And I'm sorry your dog is barking at me. But, you know, I have a black lab pit bull shepherd mix, and then there's my dingo. Dingo is an animal that's probably more like a it's like an Australian cattle dog almost. But she was taken in a drug raid, actually a drug bust on a car, and when the officer pulled over the car, he saw this dog in the back, and it had a coat hanger for a collar, and the coat hanger was cutting into it. So he confiscated the dog, and he arrested everybody. I think they got some cruelty charges. And then, of course, when he searched the car, they found all kinds of drugs in there and paraphernalia as well. So they got arrested, and it wasn't a pretty scene. But the dog was taken to be euthanized. And he was taking the dog to be euthanized. He didn't want to do it because he hates doing that kind of thing. And as he was driving, the dog got up on his thigh on the driver's side where he was, and it licked his face and like cuddled up to him. And he basically said, he stopped the car right there. He turned around. His name's Dan. He's a fantastic human being. And Dan turned around and said, I can't kill this animal. And next thing I knew, we have a dingo. All right, and the dog has been a faithful companion. It is such a good watchdog. If there is so much as a squirrel across the street running on someone's lawn, dingo sees it. And she's a herder. She likes to herd things. And we put her, I'm going to do some processing, by the way, on this flame right here. We actually took her to a boarding place to be boarded while I had to go on a trip. And the dog ended up controlling like pit bulls. And the dog was actually being very domineering. And when I went there to pick up the dog, the woman said, will you please come out here? I said, yeah, what's the matter? She goes, well, your dog is actually taken over out here. And we can't have this. I went, what happened? Well, your dog has basically, well, she said, just come look. I go out there, and she couldn't even talk. I look up, and there's like a jungle gym for dogs. It's a big wooden ramp, and at the top it's flat. And there's Dingo up there with every single yard toy from all the dogs. And she's up there guarding this entire stash of toys. Any dog that would try and come up there, she would bark at it and make it go back down. And these are pit bulls. And the woman looks at me and says, I've never seen this before in my life. I go, you know what? It's the first time for me too. And I said, Dingo, get off of there. Come here. Come down here. And she saw me. Oh, hey, it's you. And she came running and was very happy. It was so funny. So that's the kind of dog she is, you know. Amazing animal, but a little on the obsessive side.
We don't deserve dogs.
Well, remember, the whole planet belongs to mice. Haven't you seen Hitchhiker's Guide to the Galaxy?
It's been a long time.
Okay. Yeah. We belong to the mice, you know.
Oh, that reminds me of that movie Never Cry Wolf, where the biologist went to Alaska to study wolves, and he was wondering what the wolves were eating because everybody thought they were killing and eating the caribou, but there weren't any caribou around. And he discovered this was the little four-eyed guy from American Graffiti in the movie The Untouchables with Kevin Costner.
Okay.
He was playing the biologist, and well, he did some experimentation. There were a lot of mice around, and he watched the wolves one day, and they were living on mice, so he thought he would try living on mice too. And he had mouse fricassee and mouse on toast, and mouse casserole, and you name it. And he figured out that the wolves were living on mice most of the time, not on the caribou.
Wow. Yeah, you know, I'll let someone else do that experiment. I don't. I watched somebody do a survival show, and when he saw these rats and mice, he thought those would be the best thing on planet Earth, and he just couldn't stop eating these rats and these mice. And I was like, okay, no. How about no? No.
Yeah,
No.
I agree.
No way. You know, and then Tron Man says mice are cute. You know what, they are, but not when they're chewing your wires in your wall. And that's kind of a problem I have. I don't like to kill things, so I would actually opt to, you know, live catch them and release them a couple miles away. And I did that actually for a very long time. Still do. I had this one mouse that got caught in one of my live capture traps. And before I let him go, I painted his tail on the top near the back side with a fluorescent orange dot. And I say, Ted, thank you so much. Wow. How about, oh, okay. I won't mention 42, Life, the Universe, and Everything. 42.
Right.
And so I painted this mouse with this tail with this beautiful fluorescent orange. Kind of like the color Ted has there on the screen. And I let the mouse, I took the mouse for a ride 2 miles away and let him go. Do you know what? It took him 3 days. And I caught him again.
I believe it.
Yeah. I don't know how they can go that far and how they know to. And then I actually had some snap traps, which I had, and I had set up just one, and I didn't even bait it. I didn't really want to catch anything. And unfortunately, next morning I came down and little orange tail was in the trap.
Oh no.
Yeah, and I was actually very sad, you know. I was very sad. And I just sat there with him in the trap. I must have sat there for an hour, you know, just looking at him and kind of, you know, I mean, I know that's silly. People think I'm nuts, but I was like kind of apologizing to him. You know, I'm sorry. I can't believe I let you go. I gave you a chance, you know. You shouldn't have run across the trap. I didn't want you to run in the trap. And I thought, why did I set it? You know. Well, anyway, when they actually cause problems in your house, then you just want them out. So I think the snap trap was like a desperate move because I had a number of them that were causing a problem. In fact, I had a 300 dog bones, dog biscuits for the dogs that were in one of these milk bone boxes, and I ended up having a rat that snuck into the house. And when the rat snuck in the house, the rat actually found the box of biscuits. And it took him one night, from like probably midnight, 1 o'clock when I went to bed, to find that box and empty it of every single bone by 6 o'clock the following morning. There were 300 bones in that box.
Wow.
There wasn't a single bone to be found anywhere. I mean, somewhere in the walls are these things. There's a big pile of them somewhere.
I'm sure.
And I didn't know how he got in the house until I started looking where the water line comes into the house. He drilled a hole in the side of the cardboard sonotube that comes in, which goes below the concrete pad in the house, and came in through that way, which means he actually drilled a hole through all the ground. He drilled a tunnel. Like it was I mean, he should have been in Stalag 13, you know, with Hogan. And he actually drilled this hole, built this giant tunnel. And I have a little endoscope thing that I bought online, and I just ran this thing through the tunnel. The tunnel went like 6 feet, you know, and then I couldn't get the thing further in to see where it went. But they are very industrious.
Oh, yeah.
Yeah, you know, and it wasn't one of these rats that has all this nasty looking oily thing. It was actually a very pretty rat, the kind of rat you'd keep for a pet, you know. So it wasn't one of these ugly bucktooth varmint types. It actually was a very good-looking animal. So I didn't I didn't Deesman says, Mark, you know Dingo did it and blame the mouse. That's funny. I didn't catch it yet, but I did stuff up all the holes with this. And basically, it's like rat razor wire. They can't chew it. They can't get through it. It's this copper mesh stuff. So basically, it's a deterrent. Keeps them out. I mean, I don't want to kill them. Just stay out. Anyway, that said, I want to take us to a few different places now. We've been streaming for just over 2 hours 15 minutes, 2 hours 17 minutes. I'd like to show us some of the objects up in Leo and Virgo. What do you think?
Sure.
Okay, so that means I have to run out and move the dome a little bit more.
Uh-oh.
Okay, actually what I'll do is this. I'll take us to one of those places first. So let's go to our favorite planetarium program here. We will back out, and now let's move the view. Okay, and this is Cancer up here, and if you really want to know if it is, you just have to turn on the mythology imagery, and then turn it off when you want. And then right next to Cancer is Leo the lion, and here is the lion's mane. It's a reverse, it's a sickle here. Down here is its lower chest. That's Regulus. That's the star. That's the brightest star in Leo. And when you look at Leo in the sky, basically you're going to see this sickle and this triangle. That's what you see. And then that tells you that you're looking at Leo. Okay, and of course, that's the back end and tail of the lion, roughly, that you're looking at there. However, Leo also is home to spectacular deep sky objects. Okay, and we'll look at some of them tonight. And every star you see here in the screen in the planetarium program, and actually have many databases loaded, so we actually see very faintly into the sky. But all these stars you see are in our own galaxy, and we're peering through them and past them to galaxies that are sometimes between 10 to 15 to 30 to 100, almost 100 million light years away. So whereas this, like, okay, if we have like this star right here, okay, this star right here is a star that's about 1,000 light years away from us. Okay, it's 1,083 light years. So we're seeing it as it was 1,000 years in the past. But then we have M95 here, this galaxy right down below. All right, and that galaxy is 32 million light years away. So whereas we see this star just over 1,000 years ago, we're seeing this galaxy as it was 32 million years ago. Just right there in the sky. Isn't that incredible? And I really think that's amazing. So what we're going to do, and if you you watch our view here, when I take us to this new spot in the sky, we see the telescope moving now. If you look down here, you can see the telescope moving into a new spot in the sky. And this is why I got to move the dome, because it's going to move its way too far, see? And I have to, it's now looking, it's too close to the dome. So I got to go move it. All right. So I'll take a test shot anyway, just so you can see. 25,600 at 15 seconds. All right. And let me just bring up my telescope operations. The telescope has stopped moving. So let's just take a picture now. And technically I'm on M95 right now. So let's go make sure that we can see a semblance of M95. We're probably going to see a little bit of the red too, because I think that we have a little bit of the dome in the shot. And we do see just a little bit. But there's M95 right there in the middle. Okay, so Daryl, I will be back in just a minute. I'm going to go move the dome if you don't mind.
Very good.
All right. I shall be back, folks. Give me
Hey,
about
Mark,
30 seconds.
before
Yeah,
you leave, could you put that pictogram, put the image of Leo back up, or will that mess up your pointing?
absolutely doesn't. Because I don't,
Okay.
how far in you want me to go? You want me to go in?
That's pretty good there, or back out just a hair. And
Okay.
if you wanted to put up that mythological picture, there you go.
Okay.
I'll talk about that while you're gone. Then we
Excellent.
can go back to M95.
Yeah, because this is the constellation that's going to dominate the spring sky. That and the one next to it, Virgo. But all right, I'll be right back.
Very good. Folks, if you look at that, as Mark said, there on the right side, the head and the mane of the lion, that's called the sickle. It looks like a big backwards question mark. If you go out this time of year, about this time, if you look up pretty high in the east, you can see the whole figure of Leo now. And that sickle, as I said, represents the lion's head and mane. It looks like a backwards question mark with Regulus being the dot at the bottom of the question mark. If you hold your hand out at arm's length, that's about as big as your hand. If you've ever heard of the famous Leonid's meteor shower, that happens right inside the sickle, up between that star Algeba and the next star up a little bit to their right. The radiant point of the shower is right there inside the sickle. And on a good year, they just come streaming out of the head of the lion like you wouldn't believe. It's really cool. Back in 1998, I was bombing down a back road way out in the back end of El Paso County here in Colorado, east of Colorado Springs. And Leo rose right in front of me. This was the peak night of the Leonid meteor shower. The head had just poked up over the horizon at midnight in November, and it looked like Roman candles going off. Meteors were just coming out of the head of Leo constantly, and they were every color of the rainbow. They were very bright and very colorful, and some of them were blowing up. One of the neater things I've ever seen. At the other end of Leo, over there at that triangle on the left-hand side, you see where the tail is. The star's name is Denebola. You might have heard me talk in the past about other stars that are named Deneb or have Deneb in their name. Well, unsurprisingly, Deneb means tail. If you look at the Northern Cross, that is a constellation Cygnus in the summer sky, the star at the head of the cross, or the tail of the swan, is called Deneb. It's a very bright star, and it's very far away. There's another one in the constellation Cetus the whale. It's called Deneb Kaitos, which means the tail of the whale. And that's what a Deneb is. It means tail. And Mark is back just in time.
Cool. I didn't, obviously I couldn't hear what you said, but I was moving the dome in such a way that we'll be able to look, I think, both at Leo and in Virgo here.
Super.
Because there's a lot of stuff in Virgo. But let's go back now to where we were before, and that's M95. M95 is an interesting, it's a galaxy. It's actually a galaxy called an SB. What's that? Well, it's actually a barred spiral. It's capital S, capital B. You see the indication actually up here on the upper left-hand corner. I know it's kind of hard to read that, but it's a spiral galaxy that has a bar of stars, an extra bar, a long bar of stars through the center, instead of a round nucleus like the Andromeda galaxy has. And that round bar is what we see when we take photos of it. Let's go check out the galaxy, see if we can see the details. So off we go. And I checked to see if the moon was still up. It was just set, so we should be okay. I'm going to go 20 seconds at 25,600. And if I recall, it was a little bit lower in this field. Let's go. See, it's here. So I'm going to bring it up and to the left a little bit. Okay, so let's go back here. Then go there, and now we're going to bring it up. And I'll bring it up a little. And bring it up, and we're going to bring it to the We're going to go west a little bit. Okay. That should be good. Okay, telescope is settling out. Give it a couple seconds because we have something called backlash in all gear drives, all the drives. So we want to make sure that that is out. So let's do 20 seconds at 25,600 ISO. And for those of you that have looked at some of the photos I've taken within the telescope, we actually get rid of a lot of the noise, and I actually have special algorithms that will do that. And you'll see the noise actually when the image is being processed. If you're quick, you can see it being processed. So like here you can see the dots going away. This is the color noise, all right? And if we look at, say, this previous shot and then come back, now look, see all the color noise being processed away, ready, bam, see it goes away. So we're getting rid of much of the color noise on the fly, and that's a good thing. So here is this beautiful galaxy, M95, and if we do a little processing on it, then it's possible that we might see, and we see the spiral arms in this galaxy. It's really pretty. Let me just zoom in on it a little bit. Okay, there you can see the spiral arms. See them? You see those, Daryl? When he's off mute, he'll tell you.
Yes, it's a barred spiral too.
Yes.
Isn't it?
Yep.
Yeah, you can see the bar kind of running from about
11.
Well, I thought it was running like from lower left to upper right.
Oh, well, you know what? Maybe so.
Kind of about 8 to 2.
Yeah, where is it? Not sure. But
Yeah.
we'll have to look at it. I actually did a number of exposures of this particular galaxy and stacked many images together, and I do have a finished version of this that I will spring on you, along with Thor's helmet, which I took the other night, and Daryl saw the Thor's helmet result that we did. And Thor's helmet's a Wolf-Rayet star, very powerful, massive star with lots of powerful stellar winds, and it has this big bubble of gas around it that were part of it at one point. It was the star's envelope, the outer envelope. But man, I tell you, it's just amazing how these things work. So this galaxy, like I said, is there's a 32 million light years away, really, really distant. And you don't have to see just one galaxy in an image. Like if we come to this right here, this group, okay, let's do this. Let's take ourselves over here. This is like around the region of what's called M105. Okay, so we're just going to move up a little bit, and let's go and see what that looks like. Okay, you can see the stars moving as the telescope is directed to move over slightly. And then when the telescope gives us back our north, south, east, and west, we'll be set. And it'll eventually do it itself, but I'm impatient, so I'll just tell it to stop because I know we're here. Okay, we're there, Ma. Let us out of the car. All right. So I'll do, on this one, I'm going to do it at 32,000 ISO, just as a test for 20 seconds. And we'll see how much detail we'll capture in all of these that are there. So let's just bring that up and go for it. Our telescope should be set. We are set. All right, so we're taking a nice shot here. We'll see what we get. So these galaxies, we had on SkyTour Radio, we actually talked about galaxies, and we're thinking about doing it again. I'm thinking at this time, though, I'm going to talk more about active galaxies that are doing things that you can't imagine. Okay, and so galaxies like, for instance, this group right here. These galaxies are probably all very close to each other, and I'm going to move them up and take a picture again. But let's first go back into our our wonderful planetarium here. Okay, so we're looking at M105, which is on the right. Okay, M105 is 31 million light years away. Beautiful galaxy. And then this one here is 26 million light years away. But then this one down here, okay, check this out. Okay, this one's 80 million light years away. A lot further away. And it kind of stands to reason. Look how big this is. They're all fairly similar galaxies. This one is smaller because it's so much further away. Isn't that incredible? Yet in the sky, they look like they're right near each other. But you're looking at the light from this one 80 million years ago. The light from this one, okay, 26 million years ago. Right? And the light from this one, 31 million years ago. Isn't that crazy? You're looking at, this is like looking back in time. The light from this one, left this galaxy. Left this galaxy before the dinosaurs were killed. That was 65 million years ago. But the light that you're seeing left this galaxy before that. Absolutely incredible. You know? Absolutely incredible. In fact, 20 million years earlier, before the dinosaurs were killed, the light that you see left this galaxy. So that's how big a time machine the universe is, and it's really incredible. You know, it's just an astonishing factoid to actually let your brain wrap around for a second. You know, amazing stuff. So if I come back now, and let's just raise this one up a little bit more. Okay, bring these up into the view a bit. Okay. Up we go.
Mark, that's actually called look back time, isn't it?
Yeah. That's yeah, you can call it. I've heard it called look back time. I've heard the universe called a time machine. You know, it's all, but it's all very true, you know, and that's what's incredible about this. We'll just take another 20-second photo at ISO 32,000. That's the sensitivity we're using now. Okay, and now we'll see what we get. And then we'll come back, and when we come back here, let's just check it out. So look at that. Now you can see, look how bright these two galaxies are. 31, 26, 80 million light years. All right. Just, it makes it pretty, it's pretty obvious, you know. So I like the fact that these galaxies look the way they do. You can actually see spiral arms in this galaxy pretty nicely. Okay, this galaxy here would require a little bit more processing to show, yet it's brighter. But sometimes the spiral arms are more knotty and more, as in K-N-O-T-T-Y, not N-A-U-G-H-T-Y. Okay, not naughty, but knotty. And sometimes that makes them show up better. And sometimes the galaxies have low surface brightness, and which makes it problematic as well. But you can see the extended stars from this one, the extended stars from this one, its spiral arms. And then these spiral arms actually show up pretty well too.
Would it be fair to say, if you assume that all those three galaxies were comparable in size and brightness, that if, to round some numbers off, the galaxy on the lower left, if it was 3 times farther away, that it would be 1/9 as bright? Inverse square law and all that?
Yes, that's right. And let me just take a moment to explain that, because I know most people have heard me talk about this, and probably even you on our stream. But the fact is that light operates in a strange way, and so it means that if you're twice as far from an object, the light is 4 times fainter. 3 times farther, it's 9 times fainter. 4 times, 16. 5 times, okay. So it goes on and on. So the fact is, 25. So if you, what is that? We noticed that the light falls off or gets dimmed by the square of the distance away from the object, that you are. And that square of the distance is a very famous law that was discovered. It's called the inverse square law, 1 over r squared. And so this is what we're seeing with light from galaxies. So this is 80 million light years, okay? And it has a total brightness based on the aggregate brightness of all the stars. So does this one. So does this one. You can't really see the difference between these two galaxies. And really, you just sort of look in the nucleus if you assume they're kind of similar galaxies. Note this is much dimmer, like Daryl just said. And we could expect, by knowing this is 80 million light years away, we could expect that it is dim by a certain brightness, by a certain amount that we can actually calculate. And that's if they're about the same type of galaxy. And I just think that that's an excellent point you made there, Daryl. I did want to just make sure you got the kudos from me on that one. That's good.
Oh, no problem.
Yeah, and now let's go back to our planetarium program and see what else we can see. And by the way, now that we're in Leo and in the Virgo location, if those of you who know these constellations in the chat would like to see anything specific, this is where you can put in your requests. And Daryl, if I can ask you to monitor that while I'm looking around for some things, unless you have a request that you would like to see.
Oh, since you're in the neighborhood, after 95 and 96, how about 65 and 66?
Yeah, that's true. We are in that neighborhood. That's the triplet you're asking me for.
Uh-huh.
They're right here. See those 3 galaxies? This is the Leo triplet, and I believe that, okay, this is M65, this is M66. And what's the M? M is Messier. What's Messier? Well, Messier was a man, Charles Messier, and he cataloged objects in the sky that are not to be mistaken for comets. And thus we found that we have objects that are just beautiful that for him were just not comets. He was a comet hunter. So in an effort to show us what not to look at, he gave us things that we just can't wait to look at.
Absolutely.
Yeah. So
110 are the best things to look at in the sky. He did miss some nice objects, though.
Yeah. Well, that's probably because of where he was located. He probably didn't have that. That view,
Right. And he didn't own a very good telescope either. I've said before, a lot of the things that he saw through his telescope, he just called clouds, nebula in French or Latin, I suppose.
Yeah.
But there are some, surely he knew, what he was looking at was not a comet, like M45 Pleiades, for example, which is the Seven Sisters, of course. I mean, even he knew that because the ancients knew the Pleiades back in, a couple thousand years ago.
Yeah.
But he labeled it anyway.
Yep. Well, that's, unfortunately, he was a victim of his own technology, and that's something that, I guess we can always talk about forever. We're victims of our own technology right now. I mean, we have the inability to see exactly what's going on in between galaxies. And when I show you this photo, when we take this photo here, I'll tell you, I'm gonna automatically assume that we want to bring this up a little higher. Oh no, actually, yes, maybe actually. Okay, let's just take this picture. All right, so we're gonna take this picture again, 20 seconds at 32,000, and we shall try and figure this out. There's something I'm trying to show you here.
Mark, may I answer a question while you're looking there?
Yes.
Julian, the expansion of the universe affect the brightness of galaxies? It does. A lot of that when you get out to significant redshifts far out in the universe, well, the redshift, I think, actually, it turns them from blue to red and probably dims them that way. Mark Julian was asking, does the expansion of the universe affect the brightness of galaxies?
Oh, I see. Actually, as you just pointed out, Edwin Hubble noted that when certain galaxies were looked at in their spectrum, they seemed to have spectral lines that showed that they were shifted from where they should normally be. And this turned out to be a shift toward the red end of the spectrum, and we call that a redshift. And it turns out that the more distant the galaxy is from us, the more the redshift. So this became I guess what's the word? I guess it's a kind of a cause célèbre for Edwin Hubble to try and figure out what was causing the redshift and what it meant to us. And what he figured out was that by looking at this redshift, you can actually calculate how fast the galaxy was receding or heading away from us.
Yes. And
recessional velocity was something that was sort of a new concept at the time. And he calculated it based on this redshift. And actually, you'll notice in our planetarium program here, let me see if I can see that it's here. You'll notice here the lower parameter here is redshift. We're seeing the redshift parameter right here. And you can use that redshift to calculate this distance as well, basically, because the larger the redshift, the more distant the galaxy.
That relationship is called the Hubble constant, is it not?
Yeah, there's a relationship to what's called the Hubble constant, and the Hubble constant isn't. There's some research out there that indicates that the Hubble constant may have changed or be changing. So that's something we're going to have to deal with at some point. And what does that mean to us? Well, it means that the universe is either a lot bigger than we thought, or it's not changing as much as we thought. I mean, so here's mention this. When we look at these galaxies, and I'm going to take another picture to show you. I'm also going to move us that galaxy we saw at the top of the screen here when we went here, just quickly to show you that here, this galaxy right there. Okay, that one is actually this galaxy right here. It's the hamburger galaxy. You saw the buns and you saw the meat in between, the patty. Okay, but I want to actually bring us to here, and right almost out of the view is the rest of the Leo triplet, of which the hamburger galaxy is the third component. So I want to bring us there. So I'm going to move us down just a hair to here, and we'll actually see the motion here as we move. You'll see that going. And then it'll be moving a little bit because I want to show you the triplet that's here. I'm sorry, the galaxies that are here. There's a reason. I have something to talk to you about for that. Okay, we're done moving. I'm going to move us up a little bit more. All right, let it settle down, and we'll take a photo at 32,020 seconds. Okay, so the bottom line is we've had some really interesting discoveries that were made, and many of these discoveries came in the wake of discoveries of fast radio bursts. And these FRBs, fast radio bursts, are odd millisecond pulses that come from really, really far away. Okay? And so when we look at, say, galaxies like these two, which, if you'll notice, you're going to see some beautiful spiral arms right now. See the spiral arms in this galaxy? Actually stunning. Okay? And these are processed images that I just processing on the fly. Okay? So this galaxy and this galaxy, okay, is part of the Leo triplet. Let's just go back to remind ourselves of this. Okay, this galaxy here is 35 million light years away, and this galaxy here, okay, is in part of the Leo triplet, is well, how far away is that one? It's not giving me a distance for that one. Okay, well, it's going to be similar to this one. And I don't know why the distance is not given. I actually found errors in Stellarium I showed you before the other night. We could calculate it from the redshift, but I'm not going to do it because that's just time. But anyway, we're looking here at 35 million light years. And if we look at the redshift value, it's 0.0023. And what's this redshift? 0.0025. Okay, so this galaxy is slightly further away than this one. Okay, its rotational velocity is slightly higher than this one, and so that tells us that the galaxies are nearly the same distance. Okay, but let's just go back now. Again, we're talking about 35 million light years away. So if we come back to our little our view here, okay, here's what's interesting. Let's suppose that a fast radio burst came to us from this galaxy or this galaxy. Let's pick this one because we know the exact distance, 35 million light years. Well, between this galaxy and us is a whole lot of nothing. These stars are in our own galaxy. These are in the incredibly close foreground compared to that galaxy. And as that fast radio burst is heading here, the light from that fast radio burst is being affected by anything that it passes through between here and us. Okay, so over a 35 million light year distance, if there's anything between the galaxies, between our galaxy and this galaxy, it is going to affect the light. And guess what? We discovered that by looking at the light that comes from these fast radio bursts, we can tell what it's passed through. And that parameter that gives us that information is called the dispersion. D-I-S-P-E-R-S-I-O-N, dispersion. And that dispersion basically changes the timing of when the light pulse arrives to us. That is to say, a frequency of light within the light pulse. So, light we know is made up of red, orange, yellow, green, blue, indigo, and violet light, plus the invisible infrared at one end in the red, and the ultraviolet at the other in the blue. Well, maybe some of the red light is being delayed, and maybe it's being retarded in a way by something that's between us and that other galaxy, in that galaxy that's emanating this fast radio burst. Well, that will cause the light pulse to be dragged out a little bit and be larger than it might otherwise be. Knowing that, we calculated dispersion, and that dispersion is something that will allow us to figure out just what we've passed through. And so we've discovered that the galaxies, like these two together in the universe, they look like they're separate. The stars end here, and okay, that's all there is. And then the stars end here, and that's all there is. Okay, over here and there. Well, guess what? Turns out that these galaxies have huge gas tails and halos of gas that they're all within. So they're massive gravitational wells. They're huge gravity concentrations, and so any of the massive amounts of gas in the universe are attracted to the galaxy, but the galaxy is also moving. So these lines of gas get dragged behind them in their big tails, wispy tails that are behind the galaxies, around the galaxies. And so by looking at these fast radio burst dispersions, we can figure out what the gas is. And we can figure out a lot of what's going on. A lot of it is hydrogen gas that's floating out there in between the galaxies. Absolutely incredible, you know. So, and I just I wanted to say this is actually a beautiful image. If you notice right here, okay, in this galaxy image, let me see if I can zoom in a little. Okay, you'll see there's a dark lane in this galaxy with a star right there. That star is most likely, obviously, in our galaxy. We're seeing past it to the galaxy beyond. Okay, and you can see the modeling here in this galaxy's spiral structure. It's really pretty. So this is what SkyTour LiveStream is all about. You're seeing faint things you could never ever hope to see with just your eye. And even looking through a telescope, you're not going to see the image of a galaxy looking as good as this. And now, of course, that makes Daryl say, "Oh man, I don't want to hear that." But he knows it.
It depends on the galaxy.
Yes, it does. Okay.
I'll qualify it that far.
Yeah, you can say that. Okay, but I can tell you this. You may be able to pick up the dark lane in this galaxy if you're lucky. But look at the dark lane. You see that? It's really pretty.
I was going to ask you about that a minute ago and forgot.
Yeah. Beautiful dark lane. Okay. And then you see there's dark modeling in here. So this has spiral arms. I'm wondering if this is a barred spiral, actually. I think, is this a barred spiral, you think?
Kind of looks like it.
It does, doesn't it? Let's go see. We're gonna
Stellarium tell you?
It may. Let's go see. Yeah, it's a SAB.
Okay.
So basically what that means is it's a tightly wound barred spiral galaxy. According to like the Hubble tuning fork.
Uh-huh.
Wow. Wow, that's, well, I just want to stop for a second and say, hey, hi, Dee Dee. I got to tell you, if you have chest congestion, I know what that's like. It was weird. I had that too, and I had to actually do my best to carry on. I actually had to cancel a SkyTour radio show because of the congestion and everything a couple weeks back. And last week was our 52nd show, 1 year of SkyTour radio. Many of those shows were 1 hour long, but then people started asking for 2 hours. So my show's been moved to a 2-hour format, which is really kind of cool. So we had a good time with that. We still do. All right, so now back in here, this is our galaxy photo of these two galaxies. I really love, like I said, I really love this dark lane here. That's just beautiful. Just stunning. So let's go now and see if we want to look at something else. I mean, Daryl always wants to see other things, so let's go see if we can do it. Let's go see if we can do it.
I didn't see any other requests. I could think of some if you really wanted, suggestions, or I know your head is full of this stuff too.
Oh, sure. We can have a lot of fun. But here we should see 4 galaxies. Or actually, 1, 2, 3, 4. We should catch 4 galaxies in this view if we can just get right there. So let's drag ourselves over there. And let's go and grab that. Yes. Okay. So now telescope's still moving, hasn't come to rest yet. I like that it does now and then. So I will stop because I know we're there. I see the stars pretty much staying. I'm going to move us up. Okay, that's about it. And now I'm going to take this picture after stability. 32,000 ISO for 20 seconds. Dee Dee, you can also try some essential oils. There's some beautiful oils that you can get, which really can help you with that congestion. There's one actually called Breathe. It's a combination of oils. Okay, let's see here. All right, let's go and check this out. What do we got? What we get? Wow, look at that. So we have, here's the 4 galaxies. You can see them right here. Let me just do this. Okay, so you can see 1, 2, 3, 4 galaxies. They showed up just like that. Again, each one of these galaxies could have billions of habitable planets in it. Each one. We think that we may have billions of habitable planets in our galaxy. And we're just sort of a moderate-sized galaxy. We're not huge, but we're not small either. We're kind of in the middle. The Andromeda Galaxy has maybe 1 trillion stars in it, and we don't have 1 trillion stars. We may have 100 billion at the low end, and there have been some estimates that take us up to as high as 400 billion at the higher end. But, it may or may not be the case that we have that going on. But who's to say? Anyway, Now let's. I'm just having fun zipping around all these different places. So, Daryl, do you have another one you wanted to look at in particular?
Oh, goodness. I bet you could guess which one I would ask for. It's in Virgo. It's not in Leo.
Oh, you want to look at the
You're
jet?
doing fine.
You want to look at the jet of M87, probably.
Well, yeah, the M65, M666 view you had a minute ago looked like it was pretty crisp tonight. Maybe you might have good luck with the jet in M87.
Yeah. Okay. Well, why don't you tell folks while I'm going to image here, and why don't you tell folks about the jet, and I'll take us over here to this particular set of galaxies first.
Okay. Well, people, M87 is another Messier object. It's in the Virgo cluster of galaxies. It is, there are, I forget how many, many hundreds, if not thousands of galaxies in the cluster. And M87 is one of, if not the biggest galaxy in the cluster. It's an elliptical galaxy. It just looks like a big ball of stars. Looks like a globular cluster on super steroids. It is many times larger than the Milky Way. And there is a supermassive black hole in the middle of M87 galaxy, which is shooting a jet of energy right out the side of the galaxy.
Yeah.
And it looks like a tail sticking out of it or something, and it's really cool to see. It's a lot easier to image than it is to see. I think I read somewhere the other day only one person, surely more than now, but once upon a time only one person had ever visually detected the jet. And we have caught it, Mark has caught it a couple of times that I recall. One night I thought it was fairly clear, and the other night it was kind of getting lost in the noise on the screen, but you could still see it. And James Dugan had once asked about this jet coming out the side of M87. I looked it up, and it's like about 2.5 times longer than the entire Milky Way is across.
Yeah, it was
like 250,000 light years long.
Yeah, it's a fascinating object because you don't really understand or think about why this jet actually is occurring, and it's got to be something long term. Something that's been a long term effect, and that's actually pretty cool. I really like that. So let's just see here. I'm going to get to the search, and we'll do M87. I don't remember exactly quite where it is in there. And
it was in your screen a minute ago.
Yeah, no, I have it right here, but I just wanted to.
Oh, okay.
Yeah. All right, so there it is. That's M87. M87, it's when you see it in an eyepiece, it's somewhat disappointing, and the reason because you don't actually see spiral arms, you don't see dark lanes, like the Hamburger Galaxy had a patty in between two buns, kind of a thing. You don't see that. They're really a nondescript, fuzzy object. And probably, I think I just have to say, part of the problem with that is that we actually don't understand what's causing this jet in M87 actually, and that's kind of a problem for us. We don't know why this is happening, why we're seeing this jet, and
I would wonder that the usual answer might not be like you often see depictions of black holes and their accretion disks, and it's shooting jets off like the rotational pole of the black hole.
Yes.
There's something like that, but good God, that thing has such tremendous energy in it. I mean, what could be doing that?
And what could
unimaginable.
What could be surviving that?
Exactly.
If there's life in this other galaxy, is it even surviving it? That's the question. We don't even know. All right, I'm gonna just do a test here. I'll go 10 seconds because I want to see if I'm getting the dome in the way. right now. On my screen, it looks like it's in the way, but I have to check. So just a 10-second shot to confirm that. And if it is, I'll go move it. All right, it's not. You see the noise cancellation, all the noise getting removed. There's the there's M87. So what I'm going to do is I'm going to go back to our view here, and I'm going to bring M87 up a little. All right, so we'll come up here. We'll settle out, and now what I'm going to do is I'm going to take us all the way to 20 seconds at 32,000 and see what we get. So that jet that Daryl was talking about, it really is an object that makes itself very evident, and when we zoom in, you'll actually see it. The cores of these supermassive galaxies, we've thought for a long time, are as big as they are because of the fact that there's a supermassive black hole in the center of these galaxies that is causing, I'll say a little movement there, that's causing the galaxy to remain intact, and is also responsible for much of the goings-on in these galaxies. And if that's the case, then I think that we really want to consider that this galaxy having something like that going on means that there's probably a huge impact to everything in this galaxy that may, for instance, be trying to, for instance, have or engender life developing there. We might not be able to have that. We might not be able to have it if we're looking at something this crazy. You know, there might be a problem with life forming here. So let me see. I think
I would not be surprised if it had sterilized the entire galaxy.
I would think that could happen. Yeah. I think we see it there.
Yeah, just barely there at 2 o'clock.
Yeah. This is the jet, guys, right here, coming out from M87. I know there's some noise, and what I'm going to do is like I did the other night. I am going to reduce the noise in my image by changing this ISO. We're going to bring it down, and I think I went down to like, I'll try 12,800 for 20 seconds. Now, the galaxy won't be as bright, and some of the dimmer stars won't show up, perhaps. They probably will. But I want to also be able to show that jet more clearly. And we need a higher resolution image to do that, and this will do it. Or should, I'm guessing.
Hopefully.
Yeah. We did this last time, and it showed up nicer. So here we go. Here we come, and now we're there, and let's go see what we got. Okay, I'm doing this close-up view, and I'm also gonna set that color-corrected view a little differently. All right. Now, do we see it?
I think I see it.
I
think I do.
Yeah, there it is. You can't miss it. Look it. There it is.
Right. Okay, yeah, that is. I think that is better than the other night.
Yep. This is actually, you can, well, now it's very clear. You can't miss it now.
Right.
Yeah. So you see, folks, that is incredible. That is the amazing power that these supermassive galaxies have. I think M87 is one of the largest galaxies in the universe, is it not, that we know? There's got to be many, it could be several trillion stars in this one.
Yes.
Yeah.
I mentioned earlier that M87 is the biggest, if not one of the biggest galaxies in the Virgo cluster.
Yeah.
And folks, when you look at that right now, we are falling that way. Our entire Milky Way galaxy is falling toward M87.
And at the same time, the Andromeda Galaxy is heading for us.
Yes.
So you have to.
And that's that's local space compared to the distance to M87.
Absolutely. The local space is all falling toward the Virgo supercluster.
Right.
So the way the universe is laid out, guys, is really interesting, and Daryl's alluding to it now. But there's many, many galaxies in this view, and we stopped down the ISO, so we don't actually see all of them. I can actually shut off the processing, so we can actually see that there's a few more, okay, that are showing up here. You got one here, one there, one there. I mean, it just goes on. There's one right down here. There's tons more galaxies in here. But the thing that's interesting is there's a lot of mass there. And as a group, galaxies sometimes move together as a group. We have what's called a local group of galaxies, of which we are a part. And together, we are moving, again, together toward this whole Virgo cluster, the whole Virgo supercluster. Yet within our local group, we're also interacting with each other. So the Andromeda galaxy is heading toward us within our local group, all while heading toward the Virgo cluster with all of us together. And so there's a whole lot of that going on. And here's the thing to keep away and keep in your mind and take this away. Nothing in the universe is at rest. Not one single thing. So, even in your body at the atomic level, the atoms, there's always vibration. There's always something going on. Nothing is at rest. This hard table, you hear that noise, I'm banging on a table. Well, if you could actually look at the space in the atoms themselves, you'd find out that the atom is mostly space, with only a few particles for the protons, a few bits of space taken up for the electron cloud. Okay, but most of the distance between the atomic particles, the elementary particles in an atom, is just air, not air, but space. Empty space, voids. But it's all moving. They're all moving. And hydrogen is the simplest atom. It has one proton and has one electron. That electron is in a cloud moving around the nucleus. And we were taught, in school when we were little, that the electron orbits the nucleus. That's not really true. And it was Heisenberg that figured this out. The electron is actually, and this is the part that we can't understand, okay, generally, most folks can't. The electron is everywhere at once, and there's actually no way to predict where it is at any one time. So if you think of an electron as a hard candy shell around the nucleus of an atom, then you don't know where on that candy shell you are at any one time. You could be anywhere, all right? Now make that candy shell just an energy and a particle or a cloud. And you don't know where there is a quote-unquote particle anywhere. And it was sort of an uncertainty. That's part of the uncertainty principle, the Heisenberg uncertainty principle. So that's the neat part about astronomy that I think is really interesting, is that we know some of the answers and many of them we don't know. So I think it's pretty cool. Now I am also we're moving here. Let's see now. I'm finding this is kind of weird because I was playing this song and it seems like the song just won't end. Okay, there's some keystroke that when I hit it, it stops the song, and I don't know why, because I'm not doing anything that would cause that. I'm not hurting it, honest. So let's go back to our planetarium program here. We saw the Virgo galaxy, and we saw that really interesting jet off of it. And now we're going to take a look at this set of galaxies. This is called Markarian's Chain. And Markarian's Chain is a very interesting set of galaxies. And let's go there. right now. Okay. So, as we're moving, I want to grab a little bit, make sure that we're still, okay, gotta get my dome cams live again. Markarian's chain can sometimes cause me heartache because sometimes the telescope goes there and sometimes it doesn't want to. But I'm thinking it probably went there now. We'll see. Tell you in a second. Okay, so let's just pull out for a minute here and. Maybe we did. All right, so now we're going to go and take a picture and see what we got. By the way, I want to thank you guys for hanging out with us tonight. I think Daryl's having a good time with all of you. I know I am.
Oh, yeah.
Yep. Cindy, I want to thank you for coming. This is wonderful. Yeah, we love having new people show up and join us on SkyTour LiveStream. I mean, we zip around the cosmos. Sometimes we focus on one object for a period of time, and other times we just move around. Tonight's one of those move around nights, you know. And tonight this is Markarian's chain that we're looking at right here, Daryl. I think I mentioned that when you were walked away for a moment. Okay. This is a set of galaxies. If you notice, there's many galaxies all in this one shot, as before. Okay, and with a little processing, we can see now that there's a lot going on here. And Justin T says, thank you for streaming. You're welcome, Justin. I'm very excited about doing this. And most of the folks know and know that when I actually start streaming, I claim, okay, I'll do 2 hours. Okay, yeah, it's been 3 hours and 13 minutes so far. Yeah. And I mean, it's a night. It's a night to remember, and I just like to keep it going, you know. But I am getting tired, and I am gonna have to get some sleep. I think, you know. I used to work the midnight to dawn shift in the observatories, professional observatory, and that was the best time, especially with the big scope. And it was an old refractor. That was made in the late 1800s, and it was about 25-30 feet long, 20-inch diameter objective lens. It was so big the entire floor moved up and down to meet the telescope, and it was a massive beast. And
I am green with envy of you.
Oh,
I have never got to look through a big classic refractor like that, like an Alvin Clark or one of those.
this was an Alvin Clark.
Always wanted to. It was an Alvin Clark?
Yes, it was.
Wow.
20-inch.
I would love to do that someday. There was a big refractor at the, I can't think of the name of it, observatory up in Denver that the Denver Astronomical Society hangs out at and does public programs sometimes. I've never got to look through it. That's one thing on my bucket list, though, is to look through a real classical large refractor.
Well, you would like this.
I'm sure.
I actually, one night Jupiter was rising, and I wanted to look at Jupiter. And refractors are very good on the planets. And on the end of our telescope, on the big refractor, we actually had a metal grating that was over the end. And that was over the end because it would actually put some patterns on the star images. And that was good. We wanted that because we were actually doing parallax studies, which is the study of nearby stars, using parallax. And you may know parallax by, when you hold your arm out at arm's length and you hold a finger up in the air, okay, and you blink your eyes, you'll see your finger apparently shifting position against the background wall. Well, if the background wall is farther stars and your finger is the nearby stars, in the same way, you could see the motion of a star against more distant stars And the blinking of the left and right eye is the location of the Earth at two ends of its orbit. Okay, so across an astronomical, 2 astronomical units of distance, from here to the sun, and the sun out to the next position of the Earth at the far end of the orbit. That makes a large baseline from which to measure these. And so that was a situation where we had to use the grading, because we also had to measure the position on the images of the stars. And that measurement had to be very, very precise. All right. And that precise measurement required this grading. Well, anyway, the first thing I would do is take the grading off. And you can imagine that in February at 3:40 a.m., that it was very cold. So you pick up the tool to take the grading off the end. The tool is, it'd stick to your hand and feel like it was going to rip off skin when you took it away, because it was so cold. So anyway, the thing that happened was, when I took the grading off, I put the grading down. It's metal. All right. Everything you touched was metal. And you could wear gloves when you weren't messing with the telescope. But when you had to mess with the telescope, you had to take off the gloves. And there's a reason why, and I wonder if anyone knows that reason. I'm probably just going to tell you in the interest of time. You couldn't afford to get any kind of fibers and stuff on the telescope objective lens. So when you were there, you had to make sure you were totally clean. So we would take off the grading, and man, there's nothing like looking down the barrel of a big 20-inch refractor with a perfect set of lenses. And the Alvin Clark refractor was actually literally one of the best in the world. When I took the grading off, now I had the full aperture used just for observation. So I looked at everything. I took photos of Hubble's Variable Nebula. I took photos of Jupiter. I took photos of the Orion Nebula with this big slow refractor. And it was just an amazing instrument. And I actually was looking visually through the eyepiece, which you might think was just a regular size, 1 1/4 eyepiece like many telescopes have. It wasn't. This eyepiece was 4 inches in diameter. You literally looked in it with 2 eyes. You looked in it you could actually be about 8 inches away and look into the telescope. Not only that.
You're making me jealous again.
Well, no, listen to this. It gets better. Not only that, the back end of the telescope was an area that was about 6 inches by 8 inches in size, square. And you held this big 4-inch lens in your hand and moved it around on this glass backplate to see different things in the view. And that is kind of crazy, because that glass backplate was actually where we would put the photographic sensor and emulsion there. So, but that was amazing. We would usually use it to focus, for focusing the program stars and stuff for the program. But what an amazing, amazing thing, Yeah, D, you're right. Just think, a few months ago, I was outside freezing the entire stream, and you would hear me going, I think I gotta go in now. I can't feel my feet, And I did that for months. So I guess I'm kind of spoiled now with the interior warmth here. But I gotta tell you, and that is this: I am doing longer streams now because of that. So I hope that you enjoy it. Again, this is Markarian's chain. It's a series of galaxies in Virgo, beautiful galaxies. Okay, and they're right here. And Markarian's chain, you can see them. Okay, and there's 2 galaxies here, one there, and one there, one there. And if we come back, okay, we see the 2 galaxies here, one there, one there, and one there. These are called the eyes. Okay, that's just the colloquial name for them. Okay, so obviously this area of the sky is just chock full of galaxies. Chock full beyond chock full. So, I guess we have to say that Virgo is the queen of the galaxies and queen of the galaxy hoarders, I should say.
Oh, yeah.
Mm-hmm.
Well, I've said before, this time of year, getting into springtime, this is galaxy season. And if you looked from Ursa Major up around, near the North Pole, uh, not the Little Dipper, the Big Dipper, the Ursa Major, if you follow it all the way down from Ursa Major to Canis Venatici and Coma Berenices and Leo and Virgo here, of the 1,000 brightest galaxies in the sky, 3/4 of them are up there stretching in a band from Ursa Major down to Virgo.
Yeah.
And when you get to Virgo, you're looking into the very heart of the whole thing.
Yep. That's exactly right. And I got to tell you, there's another thing I wanted to mention. Somebody asked a question or comment. I wanted to make a comment. Oh, Julian asks, how much does one of these scopes cost? Well, the thing about this, Julian, is you can spend as little or as much as you want. Okay, you can get a scope that can give you everything you need and give you beautiful views for about $500. If you're looking to do advanced streaming like this, okay, then you're looking at something around $9,000, maybe more. I mean, I'm kind of rounding down a little, but the fact is, this is acquired equipment that I slowly acquired over time, did what I could with what I had at the time with this equipment. The culmination of it is the remote observatory. And it took a number of years to get everything together. And then it took me prioritizing it all, guys, to actually make it happen. And that was the other thing that happened. Now, I'll tell you why that happened. It happened, and I've mentioned this before, so I'm sorry if I repeat myself with you. My friend John Zach and I our mission was to make an internet accessible observatory, where we could go out and use an observatory over the internet, and we wanted to make that happen. And we also wanted to have other people come out and be able to use it too. John ended up dying. He got cancer and he died. And I put the telescope on the shelf, basically. It was actually a gigantic box, and I just left it in the box. I couldn't get it out. John was a very good friend. We'd known each other for many years. And then I had my brush with destiny when I had to have surgery for an infection in my heart valves. And after that surgery, I woke up blind and a quadriplegic because apparently a clot had gotten away from them, exploded in my head, and caused 8 major strokes. And they put me in a coma, and I could hear everything they were saying for a week. And I couldn't communicate and couldn't get out of my body. It was sort of locked in. You hear about those terrifying stories, but I wasn't at all frightened. It was weird. I knew I was going to be okay somehow, and the reason I know I was going to be okay, I'm going to be talking about it actually, and the reason why in Las Vegas on the 25th, I believe. I'm leaving the 23rd, coming back the 30th, but I'm going to be in Laughlin, which is south of Las Vegas, at the Mega UFO Con, and I'm going to be talking about that experience. And my talk is actually called "Where Does Science Go in the Face of the Unexplained?" I've had a number of things happen that were unexplainable events that my science has no possible explanation for, and that's something that's just beyond me. I don't know how to explain it, but I'll be talking about it, like I said. But the fact is, so I woke up like that. I was in a coma for a week, and I have to say, I actually had the most clarity of thought I've ever had in my life when I didn't have a body to worry about and all I had was a brain. I was just a head. I felt like a Simpsons head in a jar. Okay? And I was so clear thinking. I was actually designing a neural circuit for doctors to communicate with me. And I would actually, quote unquote, save it and put aside the design, rest a little while, and then bring it up again and work on it again. I was building it piece by piece and saving it and remembering everything I had done, every single thing I did. It was incredible. I could see it. I was making it in my mind, and it wasn't going away. I could retain it later. That was incredible. But as soon as they started taking me out of the coma, I felt my body reconnecting, and I felt pain and all this burning. I mean, my whole body was burning. It felt like I was on fire. And my left foot still feels like that today. But you know what? You learn how to deal with these things. You're okay with it somehow. Really weird. Anyway. So when I had to learn how to walk again, learn how to talk again, learn how to see again, I did what I had to do and got myself back to almost 100%, probably 96. And I decided I'm going to finish the observatory. And so as part of my recovery, I put my mind to work designing the observatory and getting all the stuff I needed for that. And I did it. I put it together, and I got the observatory building from Canada. I built the observatory building, a dome, on a foundational platform. I had a pier made for the telescope to mount on. The pier is 150 pounds, and it's connected to a concrete pillar that I dug into the ground 5 feet down. And I did all the work myself, and except the pier I had made at a welding shop from a good friend up the street. And it was very heavy, very hard to pick up at 150 pounds. But then I did all that. I got it all in the ground. I got it all mounted. I had to wait a week for the concrete to cure. And then I built the building around it, the dome. And then I had to mount the telescope up there. Now, keep in mind, I was still not sure I could ever lift such a telescope. But I did lift the pier, but it was very hard because I hadn't gotten my strength back. But I got it on its mount. And now the telescope, obviously thousands of dollars of telescope. I relented, and I actually had someone help me lift it. But I was on the other side of it, and we were lifting it, and it was not easy. We were both going, trying to get it up in the air. And when it locked onto the base of that mount for the first time, you can't imagine how good it felt. There it was. The telescope on the mount, the building around it, I could see it all coming together now. And I was like, wow. Now, I hadn't even thought of putting a computer in the building yet, by the way. This was just giving me an observatory to look through a telescope. But I realized I want to look through a telescope, but I want to see things like this that we're seeing tonight. Okay, Markarian's change. I want to see the eyes. But I want to be able to capture them for the future and show folks. I want to show people. So that started the path of now making it an automated or remote observatory. And that took me down the path of learning how to capture imagery from a camera, getting cameras that can actually do that. Many more thousands of dollars down the line. And I'm not wealthy by any stretch. I just prioritized my funds. No family vacations, stuff like that. And then ended up making everything. It all came together with the dome and everything. And then Jude, who worked for me at the time, and she's in Colorado actually. Daryl, you know Jude. Jude had a plaque made for me and sent it to me without telling me. And when I got it, it said what I had told her. I wanted to name the observatory for my friend John. And so she sent a plaque that said John Zach Memorial Observatory. I was like, wow, that was beautiful. you know. So, it is the John Zach Memorial Observatory, the JZMO, and it's what gives SkyTour LiveStream its many wonderful views. And again, I want to thank you all for paying attention and coming here. It means a lot. John would have loved you. He would have loved all of you guys. And he would have been beside himself with the attention that his dream and mine brought and have brought you. So I like paying you attention, and you like providing attention. I think this is just a match made in heaven, guys. And John would think so.
Mark, I have to say, I admire you. You're one of those people who has followed the dream, and more power to you. I don't know how else to put it.
Oh, thanks, Daryl. I mean, I didn't mean to kind of go down, the old little mushy path there, but
oh no, people enjoy that.
Yeah, I just wanted to pay homage to my friend John, because I really don't talk about it enough.
Sure.
He was a great guy. Every time he'd come over, he'd bring a whole pack of Oreo cookies for my kids. It was like, and he would sneak them in, hide them behind his back so no one would see them until it was the last minute, and then he would throw them out on a table and run away. It's like, and the kids would go, ah, John, Uncle John, So it was kind of fun.
That's great.
Yeah. I mean, and the thing is, the thing that was interesting is, John and I wrote an image processing program way back years ago, right when, we were still using, we were using very, very, it was like 320 by 240 graphics at that time. Come on. And, but we managed to get histograms and 3D digital imagery of representations of our data from our CCD cameras at the time. And I've got to say, we were stunned to find out that the Space Telescope Institute was actually using our program to do some pre-processing on Hubble images way back then. And I was like, wow, we were amazed. And they told us, oh yeah, we use it on our on some of the programming. The imagery from the Hubble. And we had to get clarification. And I said, you serious? And they went, oh yeah, it's pretty good. And we weren't trying to make any kind of a stab in the image processing market. We were writing it for ourselves, and we gave it away free to whoever wanted it. And the Hubble folks used it for a little while, and I thought that was really, really nice. I was humbled by that. It's like, wow. So this tells you, Daryl, it tells you, and everybody listening, it tells you that, even if you are doing this for yourself, even if you're doing something that you are interested in, look how far it can go.
Oh, yeah.
Yeah.
I agree completely. I think we're lucky nowadays, with technology and all this, that you're able to bring this to us. Back when I did public programs, they were live, and I could see if I reached someone in the audience. I probably said this before. I might have 100 people in there, and if I saw that I had really connected with one person, if I saw they had that aha moment, that I felt like I had been successful that night.
Yeah, I've done that. I don't know what it is. Maybe the night sky is my drug. I've never been a drug user of any kind. I've never, done any of that stuff. I guess I'm kind of the classic epitome of a nerd, or a geek. All that mattered to me was learning more stuff. I want to learn more. I want to learn about these galaxies. I want to learn what, tell me, I want to learn more about the eyes. I want to learn about Markarian's chain. How to get its name? What are these galaxies? How far are they from us? And what types of galaxies are they compared to the Milky Way galaxy? And by the way, just what is our Milky Way galaxy? We thought for a long time it was an SB spiral, and then we thought maybe it was an SC. And then now we're we're quite sure that we're a barred spiral, something that I never even imagined we would be. But we're a barred spiral galaxy. We have an extended bar of stars through the center of our nucleus, like some of these barred spirals we saw earlier tonight. Really incredibly impressive stuff that we now know. Yeah, you know what? We can see all these galaxies out here, right? But we're inside our galaxy. See, we're still looking through stars of our own galaxy here to see out at these galaxies. Okay, these are all here with us. Those galaxies are far away, millions of light years away. These are thousands of light years away. Okay, these stars, millions of light years. So it's amazingly distant. And as I said, as Daryl said before, we call it look back time, looking back in time. These galaxies are all at slightly different times in the past, you know. But they're all millions of years in the past, all of them. And that's something that I've just never get tired of talking about and exploring. And like I said, I'm creating a talk that's going to talk about the look back and the time machine that is the universe.
Cool.
Yeah, I mean, every single thing is a time machine. You see your friend, 25 feet away. You're seeing your friend a fraction of a nanosecond earlier, or later than when he actually made that little movement. Okay, you're seeing him, at a slightly earlier time from when he actually is doing things. And everything's a time machine. Every single thing. Now light moves fast. 186,282 miles per second is 7 times around the Earth in a second. Okay, it can do the circumference of the Earth 7 times in a second. That's pretty impressive. If you shot a flashlight, toward the horizon and it could somehow magically bend around the Earth, you could not move out of the way in time before it hit you in the back of the head. Okay, at least once. It takes you 1/10 of a second to react to stimuli like burns and things. And when you watch the ultra slow motion of someone touching something hot, it seems like they're leaving their hand there forever. And then they go, and they pull their hand back. Okay? Well, in the same way, you see, our movement and the whole way the universe operates, it's crazy. There's a lot of this going on, and we live at one level, one speed, so to speak, in the universe. But the universe has time aplenty, I tell you, it's just crazy, So, yeah, and there's Dr. Mark in Texas says, Mark, when you say they stir in the past, gone now, that's very sad to me. Yeah, that's true. The universe is a massive time machine. Some of the stars we look at in the sky, even in our own galaxy, only in our own galaxy, for the stars that we can see as individual stars, some of those stars may not be there now, because in the time it took for the light to get here, say 10,000 light years away, or 7,000 light years away, 4,000 light years away. I mean, the Andromeda galaxy is 2 million light years away, and we can see individual stars in that galaxy with proper tools. But when we look at galaxies like this, well, we're only ever going to see, unless we consult the Hubble or the James Webb, we're only ever going to see fuzz that is the many stars with their combined light that we see, and so that's impressive to me. But when we look at some of these stars, like if this star, I don't know how far the star is, but let's just say this star right here is, say, 3,200 light years away. Well, stars live a long time. They live billions of years generally, but the hotter, younger stars are the bigger, bluer stars, like the O-type stars and some of the Bs. They only live a few 100 million years. So it's possible that some of these stars, some of the brighter, hotter stars, are no longer there, and we're just waiting for that light train to catch up that shows us the event that happened at some point in the distant past. And like the light of some of these stars heading for us, they could have gone supernova when Neanderthal roamed the Earth, and we won't see the light, you know, for just like a few more years or something. I mean, that's the kind of thing that I think about, you know. And that's all part of when I do that talk, it's gonna be all part of that. Anyway, I think Mercurian's chain, the eyes, this is a good place for us to kind of do the drop off now. And that is to say that I really enjoyed hanging with you guys. Had a wonderful time. Daryl's amazing as usual, and I just want you guys to know that I really enjoy doing SkyTour LiveStream with you. You guys are wonderful. You're kind of like my family now. So in a sense, I'd like to thank you for being part of that family, and I want to thank the folks that are repeat visitors, and I want to thank the folks that are here for the first time. I hope you enjoyed it, you know. Hope you really enjoyed it, you know. So I'll be here the next clear night as well, and we're going to focus on a different area of the sky than we have. I've got some ideas about which way we're going to point the dome, and it's going to be a little different because the other night I saw Vega come up, and it's Vega's just coming up now. Actually, we can see that, and that's summertime. Summer's heading for us, guys, and it will be here before you know it. And I'm really looking forward to checking out some of those summertime vistas. So I do want to say to you guys, thank you for coming by, and I will be seeing you the next clear night, and I'm sure that Daryl, if you want to join us, then you're more than welcome to join us.
Oh, probably. We will. Thank you for having me, Mark, and good night, everybody. Hope you had fun.
Yeah, I saw a lot of really nice comments, so thank you for the kindness to me and Daryl. And we will be back on the next clear night. And just remember, keep looking up, guys, because the universe isn't getting any younger. We'll see you later. Good night.
Me neither. See you, Mark.